Okay, I sent a reminder to all the people registered because we have still few participants. We can wait an additional minute, then I think we can start. For who has arrived as an attendant, yeah, we will start in 1 minute from now. Okay, I think while people is entering, I think we can start if Fred and Valeria agrees. No, so otherwise
Okay,
we get too much late. We have still few people online, but there are people also in the room. So let's I think we can cut the ribbon. Eventually, with you, Valeria and Fred, you see people in the waiting room. Please admit them directly. Okay, welcome to the Taranto Eco Forum. We are at the cutting of the ribbon of the international session 23 of May 2025. We have this really interesting program, worldwide experience in mining sites. The reason is because in Taranto especially, we have a great steel production. And this year we want to investigate also from where raw materials are coming, the impact also from the extraction of these raw materials. So the impacts are not just on the steel production plant, but also from where the raw materials come. And here today we are sharing some experiences on how to deal with mining sites, with how problems have been solved in other countries. So take advantages of knowing those case studies, those way of solving the problem, the environmental problem connected to mining sites. Is not water extraction, as you know. It's minerals have heavy metals that could be also could have an impact on human health and on ecosystems. So let's take advantage of these 8 case studies that will be presented today. First of all, let me introduce myself. My name is Marco Falconi. I work at ISPRA, Italian Environmental Protection Agency, and dealing with the contaminated sites of the national priority list, 42 most polluted areas in Italy. I'm currently the scientific coordinator of RemTech Europe. That is a conference that, let me tell two things about this conference. Will be held in September from 15 to 19 of September. It's free of charge, and you can follow it in Ferrara. It's a beautiful city in Italy, or you can follow it online. Everything is free of charge, like this webinar. So I will recommend you, to follow our website and discover more about our program. But it's with my big pleasure that I want to introduce now Fred Coulon. Fred is a close friend and also is the chair of Aqua Consol. We wanted to organize this first event together. It's like a pre-event of both our big conferences. Fred that will introduce himself and say something about Aqua Consol that is next month. Fred, the floor is yours.
Thank you, Marco. Good morning and good afternoon because we got an international attendance today. So thank you for the introduction, Marco. I'm a professor Frederick Coulon. I'm based at Cranfield University in UK, and I'm also the chair of Aqua Consol, so one of the largest conferences in Europe around sustainable land and water management. So we're very pleased to do this joint event together with RemTech, and we are also looking forward if you are around in Europe, in Liège on the 16th and 20th of June. So we're very pleased to be partnering with Marco and RemTech on such a thematic of mining site, myself looking also at resource recovery and looking at rare earth elements. So it's still highly topical even in Europe and UK. And it's great to see talk across Australia, Spain and Europe. Thank you.
Okay, now I hand over to Valeria for introducing herself, say something about Taranto Eco Forum and presenting also the institutional welcome from Silvia and David.
Thank you, Marco. Good morning to everybody. I'm Valeria Ancona. I'm a researcher at Italian National Research Council of Bari, and I work with environmental remediation techniques, and I share with Marco and Fred the theme of this international conference on mining sites, because in addition to environmental pollution, the growing demand for mineral resources accentuated by the ecological transition is causing a decrease in the availability and increase in the prices of these raw materials. Strongly expanding sectors such as renewable energy, especially wind, electronics and batteries for electric cars, require a wide use of these materials. In this context, the European Union has approved an important act, the Critical Raw Material Act, in 2023. In order to also obtain greater independence from the other non-EU nations, given the current precarious geopolitical balances and almost monopolize that exists some critical materials such as lithium, mainly produced in South America and Australia, and rare earths, mainly extracted in China. These themes is very interesting, so we are very honored to present, to have these speakers to illustrate these important and relevant case study from the world. So now, before to start, I introduce with great pleasure the General Manager of Ferrara Expo, Silvia Paparella.
Thank you very much. Good morning from Taranto. I'm Silvia Paparella. I am the General Manager of RemTech Expo, environmental technology hub that will be held in Ferrara, as Marco already said, from the 15th to the 19th of September. We are now in Taranto for the Taranto Eco Forum. We opened yesterday the third edition, an edition made of activities and actions, an appointment that was capable to bring in Taranto, in the southeast of Italy, some of the most important experts concerning the topic of energy transition, ecological transition, blue economy, water, safety, and of course, mining. Mining is a crucial topic, as we already know, and we are going to meet some of the people from the European Parliament on the 4th of June in Brussels during the EU Green Week, where we are going to organize an event on mining. Thank you very much for your participation. Thank you so much to Marco Falconi, to Valeria Ancona, to David Govoni, to Patrick Poggi, that is the organizer of Taranto Eco Forum, as me, and of course a big thanks to Freddy Coulon from Aquaconsoil. Thank you very much for accepting also the opportunity to organize this crucial meeting together. Thanks.
Thanks, Silvia. I introduce David Govoni from the European Federation of Geologists.
Thank you. Good morning, everyone. It is really a pleasure to be here. First of all, because it's more than 15 years that I come in this region, Taranto, for work, and in particular to monitor some mining activities. So I felt really honored and interested from this invitation. I'm here today to represent the European Federation of Geologists, which is a European organization that groups 27 national associations of geologists across Europe. It represents around 45,000 individuals. As you can imagine, as we know, geologists are really a key part of the value chain of mining. The colleague Valeria highlighted the importance that Europe is highlighting and putting on mining for the green and clean development of our European economy. As geologists, we stay in this path. We are really part of those contributing. I want to close this introduction just with a point strictly related to the environmental legislation and to the points of this forum. As a European Federation, we also in our official observation to European Commission, we stressed the importance of having to clarify within the legislation the figures, the people that as competent person, which is part of the mining standard definition, can work on these topics. This because these standards that define competent persons, professionals, also helps in the definition of ethical and environmental professional standards. So we are really open to any collaboration from this network, and really it's a pleasure to be here with you today at TEF. Thank you.
Thank you, David. So Marco, if you want, we can start.
Yes, we can start. Let me remind just one thing before handing over to Fred that will introduce the first speaker. The session is recorded. The session is recorded, so if you don't want to be recorded, please leave now. And the second stuff is that we encourage you to use the chat for asking questions. We can also hand over to you, let's say, for asking directly the question to the speaker. And just with this reminder, I hand over to Fred to introduce the first speaker.
Thank you very much, Marco, and a very great pleasure to introduce our first speaker, Kirsty Greenfield from Runbold, where she's going to provide us with an overview on the case study for hydroaluminium and highlighting and demonstrating how we could do sustainable remediation of aluminium from smelter wastes. Over to you, Kirsty.
Thank you, Fred, and I will start by sharing my screen. Let's make sure that is working.
Is something happening for sure? Yes, we're all good.
Okay, so I will start my presentation. Thank you. Aluminium smelter waste is a global issue, and this presentation does look at a case study of sustainable remediation at a smelter in Australia. So I'm going to talk through some of the context of the Hydro Aluminium Kurri Kurri smelter, or the HAC smelter as we call it, the assessment of remedial options, how the project progressed, and some of the key takeaways. The Hack smelter is located in the state of New South Wales on Australia's east coast. The smelter was built in 1969 in a rural area close to the town of Kurri Kurri, and it closed in 2012. The smelter layout included typical elements of an aluminium smelter. There were 3 pot lines with an associated large switchyard for the required incoming power, a casting area to cast molten aluminium, a carbon plant to manufacture carbon anodes, engineering services at an area known as technical services, and an administration area. Hydro also owned a large amount of land surrounding the smelter as a buffer zone to limit the impact of fluoride emissions on surrounding communities. Now you can see the nature of the buffer zone in this main photo. It's primarily undeveloped bushland up in the northwest, low-lying swampland and farmland up in the northeast, and rural residential properties in the south. At the time closure was announced in 2012, Hydro had a well-developed strategic vision for their land. They wanted to fulfil their environmental obligations, which would allow the smelter site to be redeveloped for future industrial land use. Hydro were also keen to see suitable development opportunities in the buffer zone, including retaining a large amount of that undeveloped land for conservation. Hydro identified early on that there were key tasks required to achieve this strategic vision, and that was demolition and remediation of the smelter to maximise these redevelopment opportunities. So what is aluminium smelter waste? The process of smelting aluminium generates a waste known as spent pot lining, which is the refractory brick lining of the pots used in the smelting process. And this lining provides a thermal insulation. So the photo on the left here is looking down the potline building at the Hack smelter, and then on the right we have a cross-section of a single pot, and the thermal insulation brick is shown at the base. Now the important thing to note here is the cryolite electrolyte. Now this material is a major contributor to contamination, as cryolite contains fluoride, which is absorbed by the refractory brick lining. Aluminium smelter waste is generated from the failure of the pot lining, which occurs after around 4 years of production. And once it fails, the brick lining needs to be removed and replaced with the removed brick known as spent pot lining. Now, all aluminium smelters across the world have to manage spent pot lining, which contains high concentrations of leachable fluoride and cyanide. In recent years, this material has been able to be reused in the circular economy. However, many smelters have legacy stockpiles like this one at the Hack smelter. This main photo shows the stockpile in the mid-1990s, and there's black leachate in the foreground that's generated from the infiltration of stormwater through the stockpile. Now, it was in the 1990s that this stockpile was recognised to be an environmental issue that required better management, and the stockpile was capped with clay in 1995, as you can see in the bottom photo. And that reduced infiltration and the generation of leachate, and from this time on, spent pot lining was stored in purpose-built sheds at the site. Now, in New South Wales, spent pot lining is managed under a chemical control order, and this was released in 1986 by the State Pollution Control Commission, which is now New South Wales EPA. Now, this order provides a definition of aluminium smelter waste, and that's material containing greater than 150 milligrams per litre of leachable fluoride and greater than 10 milligrams per litre of leachable cyanide. Now, it's also important to note that there are activities that are prohibited under this order. So you cannot process, keep, sell, distribute, convey, use, or dispose of aluminium smelter waste. And this was a major consideration for us in identifying and assessing suitable remediation options. Now, the stockpile didn't just contain spent pot lining, it was mixed with other wastes. In particular, there were wastes from the carbon plant impacted with polycyclic aromatic hydrocarbons, or PAHs, and gasket materials made from friable asbestos. So Ramboll's assessment identified that materials within the cap waste stockpile were classified as a range of waste types relevant to the local jurisdiction of New South Wales. Now, the most problematic issue here is the high concentrations of PAHs, which give a classification as hazardous waste. And there are no landfills in New South Wales that are licensed to accept hazardous waste. So again, this was a challenge for us in identifying suitable remediation options. 7 remediation options were identified for the cap waste stockpile, including doing nothing, which was never really an option for Hydro's legacy in Australia. Now, it's important to note that spent pot lining is primarily carbon and steel, and we were looking for options that would allow for the recycling of this material. So the options identified included both on-site and off-site containment with and without sorting to remove the carbon and steel. On-site thermal treatment by plasma gasification was also considered. In assessing these remedial options, Hydro and Ramboll were looking for a sustainable option. Now, in Australia, there's an Australian standard, ISO 18504, and this defines sustainable remediation as the elimination or control of unacceptable risks in a safe and timely manner while optimising the environmental, social and economic values of the work. To assess these remedial options, Ramboll completed a net environmental benefit analysis, looking at what's the benefit of each option compared to the adverse impacts, both to humans and to the environment. And this is where the key sustainability metrics were selected, and these key metrics were identified to be human health risks, worker safety, impacts to ecology, and greenhouse gas generation. Now, there's a lot of work behind this, but this graph shows the output, and the top chart shows the human health risks in blue and the worker safety risks in orange. Now, these risks were primarily driven by the duration of chemical exposure, in particular to PAHs and to friable asbestos. And then the risks associated with machinery and equipment that were used as well. And then the bottom chart shows the risk to ecology in green and greenhouse gas emissions in yellow. Now, the risk to ecology looked at the vegetation clearing required and the potential for uncontrolled discharge of stormwater. And I'll go into more detail on the greenhouse gas emissions in a minute. Now, this is the same data as a normalised graph where each of the metrics has an equal weighting. And this assessment shows that options 2 and 4 have the lowest impact. Now, these options were the on-site containment in a purpose-built containment cell, either with or without gypsum treatment. And the option that was ultimately selected was on-site containment with gypsum treatment, as this was required by New South Wales EPA. So once treated with an addition of 10% gypsum, New South Wales EPA considered that the waste was no longer aluminium smelter waste under the chemical control order, and it could be legally disposed of in a containment cell. Now, a close-up look at those greenhouse gas emissions. A comparative greenhouse gas assessment was completed in 2017, and that included accounting for all significant Scope 1 and Scope 2 emission sources for each option. Scope 3 emissions associated with upstream and downstream activities were also considered, and this was particularly in relation to the carbon and steel recycling. So this graph shows the total greenhouse gas emissions as tonnes of CO2, and is clear that aside from doing nothing, options 2 and 4, which are the on-site options, have the lowest emissions. Now, this is primarily due to the distance to transport materials off-site, which would occur for options 3, 5 and 6, compared to transporting materials from one part of the smelter site to another. Now, there was a lengthy approvals process for the containment cell, and during this process, Hydro engaged with the local community through the establishment of a community reference group and development of a website with information about the history and redevelopment of the smelter. Hydro and Ramboll engaged with New South Wales EPA to prepare the required environmental assessments, and the cell was approved in 2021. Now, the spent pot lining that was stored in the purpose-built sheds was not disposed of in the containment cell. There's a company in Australia that can treat spent pot lining with a proprietary technology, and this company recycled the more recently produced spent pot lining that was not mixed with any other waste. However, the containment cell did include materials from sources other than the cap waste stockpile. So there was contaminated soil within the Hack smelter footprint, primarily from the aerial deposition and accumulation of PAHs at the carbon plant, and from the leaking of petrol, diesel, hydraulic oil and fuel oil at both the carbon plant and the technical services area. There was also contaminated soil within the buffer zone from the demolition of farm buildings constructed from asbestos and from the disposal of general waste from smelter expansion projects in the 1980s. And then the demolition of the smelter buildings and infrastructure also contributed a small amount of non-recyclable demolition waste that was also placed in the containment cell. So the total estimate of material requiring disposal in the cell was around 700,000 tonnes. Now, the location for the containment cell was relatively easy to identify. The clay used to cap the cap waste stockpile in the 1990s was won from an area of land in the buffer zone immediately to the northwest of the smelter. This disturbed land was an ideal location based on the local geology, the depth to groundwater, and the limited clearing required. The cell was designed with the best available technology for a cell liner and capping system. Geotextiles were sourced internationally for quality control. However, the drainage aggregates were able to be sourced locally in the Hunter Valley, and the low permeability clay for the cap was able to be sourced from on-site. So cell construction commenced in 2021, and this is the area at the start of construction works. And I'll flick through the next few slides to show you the progress of works. Here's the base of the cell at the completion of lining works in 2022. Construction was completed by a remediation contractor under the supervision of an independent construction quality assurance engineer. Here's the progress of filling the cell in 2023. The total mass of waste placed in the cell was just over the anticipated 700,000 tonnes. Filling of the cell took 8 months and close to 23,000 truck movements. And here's the progress of capping works in 2023. The cap design includes a gas collection system with a single gas vent at the centre of the cell. And the majority of the cap is a subsoil layer comprising clay material that was won during the construction of the base of the cell. Here's the cell in early 2025 at the completion of works, and the grass is now growing. And there's a number of garden beds that you can see on the slope of the cell, which were designed to slow down stormwater flow over the cap surface. So this is the completed cell, and Hydro has commenced long-term monitoring of cap stability and leachate and gas generation. Now, at the same time we were capping the cap waste stockpile, we were filling the cell, the cap waste stockpile was being remediated. And the next few slides show the progress of those works. So excavation works began in May 2023, working from west to east, and capping was maintained over the waste to limit the potential for leachate generation during rainfall events. And luckily we had a period of dry weather during the excavation works. Excavation works continued through July into the base of the stockpile. And this is where it gets worse before it gets better. So this photo from August 2023 shows the waste interface with natural soil. And you can see the pools of black leachate at this interface. And the leachate was removed and treated through a temporary water treatment plant. Excavation works were continued so that we could remediate impacted soil beneath the waste. At the completion of excavation works in October 2023, one small pool of leachate remained in the northeastern portion of the stockpile footprint. So the western 2/3 of the stockpile footprint were within stiff, high plasticity clay, and once the leachate was removed, it did not regenerate. Now, backfilling works were substantially complete in March 2024, and you can see that 2 different backfill materials have been used. So the western portion of the stockpile footprint was backfilled with clay, while the eastern portion was backfilled with a more permeable material to allow for some infiltration of stormwater. And this more permeable material was crushed concrete generated from the demolition of the smelter buildings. So at the completion of the remedial works, an area of over 26,000 square metres of land in the central part of the smelter footprint is now available for future industrial redevelopment. So where is the Hack smelter at now? The demolition and site remediation project was completed in August 2024 after 4 years of demolition works and 3 years for cell construction, filling and capping. The former smelter was identified as an appropriate location for the construction of a gas-fired power plant, and that fast-tracked the reporting and sign-off of the western portion of the smelter footprint. And as you can see in this aerial photograph, construction works are nearing completion.
Christine, you are muted.
My apologies.
Okay.
Have you heard the presentation, or I've been muted?
Yeah, no, just now on this slide.
Okay. So just to finish up, so Hydro were looking to find the most sustainable solution for remediation of aluminium smelter waste. And if you're looking for sustainable remediation at your site, here are my key takeaways. So having a strategic vision for the future of the land is a crucial foundation for identifying sustainable remediation options. Now, there's a range of sustainability metrics that can be assessed, and you should take a close look at those that are most relevant to your site. And then make sure you have the data to back up your selected option. So at the Hack smelter, the containment cell seemed like an obvious solution, but we still needed to demonstrate to the government regulator that it was the most sustainable solution. And then the pathway from your strategic vision through the approvals process to the completion of works can be long and winding. So for the Hack smelter, the approvals process took 6 years, and then cell construction was delayed by a year due to heavy rainfall in 2022. But as I mentioned, the cell filling and capping works are now complete, and Hydro has moved into the phase of long-term management of the cell. So Hydro stayed the course, and we've now been able to celebrate achieving their strategic vision after 12 years of post-closure work. And thank you very much.
Thank you very much, Kirsty. Very good, great presentation. So I can't see, is there any questions in the, I can't see any on the chat, but we have a few minutes if you want to ask questions in the chat. Very interesting to see the decision making for the sustainable approach. I was just wondering whether you have been also looking at using the spent for the cement or the kiln industry. So instead of having just as a capping, would it be possible to have it as a basement for the future redevelopment of the site?
It would be possible, but the main issue that we had with that stockpile was the mix of waste. So because there was material that was impacted with PAHs, and then the material impacted with friable asbestos, this made it really difficult to be able to look at an option where you could sort and reuse the material. So ideally, we would have liked to have done that, but there was the health and safety risk for workers interacting with material was too high to be able to do that.
Right. We've got questions about who is managing the encapsulation in the future for the site.
Yeah, and that's a really interesting question. So Hydro is managing the cell for the first 5 years, and then after the first 5 years, the ownership of the cell will move to the state government of New South Wales, and the state government will manage that in perpetuity.
Okay. And you've been required by the local government to get regular or active monitoring on the ongoing use of the site? Is there potential risk of leaching that would need to be managed, or is there any particular precaution you need to put in place around this site?
Well, the good thing about aluminium smelter waste is that it doesn't generate leachate in and of itself. So the only leachate that it gets generate is from rainfall during the capping, during the filling works, and from dust suppression, where we use water sprays to keep the dust down during the filling works. So there are leachate sumps in the base of the cell, and we are extracting leachate at the moment, but we're extracting quite small volumes of leachate, and it's expected that those volumes of leachate will drop over time, and eventually you won't have any leachate generation at all. The other thing we'll be monitoring is the potential generation of gas. So aluminium smelter waste can generate methane as a gas, and we've got that gas extraction network with a single vent at the top of the cell, and we've been doing monitoring for gas, and we've not picked up any methane at the moment. So again, not anticipating to have issues with leachate or gas generation in the future.
Great. We have time for one more questions. If curiosity, obviously here in Australia, could this be applied to any size site, or is there you see limitation on how large a site could be done with this approach?
Oh, look, I think it's a really good approach that you can use on any size site. And one of the things you have to weigh up is if you don't contain your waste within your site, if you have a suitable location where you can, then you have to truck the waste somewhere else. And that's where you start generating large greenhouse gas emissions from the use of diesel to be able to move materials around. So it's definitely an option that can be utilized on any size site for the volume of material that you're able to contain, as long as you've got the right geology, you've got a good depth to groundwater, and you're not going to be impacting on the local environment.
Okay, and we just had another question, was more about the long-term monitoring and management, where how you get the funding, or what are the options to get the funding to keep the management, and because effectively it's still a long-term process. So as you've got that legacy where you need this monitoring and management of the site. So how is the plan to ensure you got the funding to do that?
Yeah, the funding all comes through Hydro. So they are responsible for providing the funding. And when the cell gets transferred to the New South Wales State Government, it's Hydro that provides the dollars to make sure that the monitoring continues.
Okay. Well, thank you very much for the presentation. That was very Kirsty. It was great, on time, and thanks also for answering the question on the spot. And we are exactly on time. So just to remind our audience also, please mute your microphone if you're not speaking, because we had some interference during the talk. And now we're going to move to the next speaker, which I think is Valeria introducing.
Okay.
Thank you, Kirsty.
Yes. Okay. The next speaker, we have to verify if it is online. Song Li Wu.
Hello, I'm here.
Hello.
Yeah, hello.
Your contribute entitled Mine Tailing Solidization Theory and Technology. So you can share your PowerPoint file.
Okay. Thank you. Let me share my PPT.
While Songling is sharing his PowerPoint, Christy, your presentation was amazing. Many questions. Can you check in the chat if you could answer some additional questions that obviously Fred cannot ask because for time constraints. Songling, sorry Valeria, I take the floor a moment. Songling, could you put full screen?
Yes.
Yeah. Oh. Is that right? It's still small?
No.
Not yet.
We see the working PowerPoint, but let's say the...
Let me check.
No.
Is that okay?
No, you have to go display setting and swap.
Okay, perfect. Perfect. Thank you.
Okay.
Forward.
Sorry for that. Okay.
No problem.
Yeah, thank you very much for Marco and the committee organizers to invite me for the presentation. And today I would like to give a talk on the work we have done together with Professor Longbin Huang, the University of Queensland, Australia. And in the last nearly 7 and 8 years, we have developed a new technology, which is called eco-engineered soil formation from the mine tailings. And here I mainly give a brief introduction on the theory and technology aspects of this new technology. As we all know, there's hundreds of tons of mine tailings over the world. And here the picture is showing in the whole world, so nearly 10,000 large tailing ponds were deposited everywhere. And these kind of mine tailings showed great threat to the local environment and also the ecosystems. And then in last year, research showed that they had used the satellite or the some other methods to say that even more than half of the tailings were undocumented. That means nearly 120 kilometers was, was occupied by this mining wastes. And our work was located in Western Australia, and there's a very large magnetite mine tailing area. And you can see in the left pictures, there are huge amounts of tailings there. And this kind of tailings mainly contain very fine particles. In the ICM figure, there are a very small surface area. And in the right, you can see there's some native soil particles. And these native soil particles, they mainly have some irregular mineral particles, which are mainly generated through the mineral resin. And actually, this kind of secondary mineral cements all the other mineral particles into soil aggregates. And this kind of soil aggregates, they are key units for the soil functionals. While this kind of aggregate structure was much leak in the mine tailings. So that's why you can say in the tailings that nothing can grow. And also, besides this, there are also some kind of, extremely physical chemistry, such as in the mine tailings, in the alkaline RO tailings, their pH are very high, with nearly above 10. And even in some bauxite radius, the pH nearly like 13 or 14. So it's much alkaline. So in some kind of tailings, like sulfate tailings, they have very lower pH, like zinc leak tailings, they have a pH about 3 or 4. And this kind of extremely physical chemistry and the leak of physical structure, they constrain the soil, the revegetation in the mine tailings. So, but we found in the mine site, there actually some kind of tolerant plants can grow in some area of the mine tailing deposited. And this kind of roots, they can have some of the functions to colonize these tailing areas, and their roots activities can enhance the mineral resin. And so we think maybe we can use this kind of functional plants and also the reservoir microbes to accelerate the soil formation processes. That means to convert the tailings into soils by nature-based solutions. Okay, this is the theory about the pathogenesis. In the nature system, from the very early began rocks, and there nothing can grow, but step by step, there's some kind of small microbes and also some biocrust. And then this kind of microbes biocrust, they can use the minerals to, as resources, and they can also accelerate the mineral resin, and also their organics derived from the photosynthesis or from the microbes can also interact with the minerals. So from time to time, the plant, more and more plant can grow, and more organic matter, and they can interact with the minerals to form the soil structures, and then with the key long-term pathogenesis, more and more ecosystem can grow, and that's the theory of the nature pathogenesis. So from the mine tailings, we think this kind of tailings actually they were from the from the rocks beneath the surface area, and these kind of rocks were ground, and there's some valuable metals like iron or some valuable other elements were extracted. Then they left lot of phyllosilicates, and this kind of phyllosilicates can be the parent materials for the eco-engineered soil formation. So that's the basic fundamental theory. And so based on this fundamental theory, we have designed a protocol on how to convert this kind of tailings into the soil-like materials. So the first, we have to, to deal with the tailings with very high extreme physicochemical conditions, like high alkaline saline conditions, and with very compact physical structures. And these conditions, no plants can grow. But if we give some extra organic matter and some kind of microbes, the tolerant microbes can grow. And this kind of microbes, they can decompose this organic matter, and they can generate some organic acids to neutralize the tailings. And also then some microbe-derived organic matter, they can be generated and accumulated in the tailings to form the earlier soil structure. And then based on the earlier techniques, some like peony plants, with especially this very tolerant plants with fine roots can colonize the early techniques. And this kind of fine roots can further advance the soil formation processes. And then further more and more native plants can grow. And these native plants can attract more native microbial communities to generate more powerful micro food web, and it can accelerate furthermore the mineral weathering and soil structure and soil organic matter stabilization processes for more advanced soil technical formation. Okay, so this is the first step. As there no plants can grow, and we give some organic matter and microbes inside. You can see this is a very proof of concept study in a small tube. Then after 1 month of the microbes decomposition of the organic matter, a lot of organic acids were generated, and the pH dropped significantly from the extremely alkaline conditions to the nearly the neutral conditions. And then actually among this kind of tolerant microbes, there's some kind of very powerful, like sulfur oxidizing bacteria. They can accelerate more on the accelerate the mineral weathering, especially the R2 beer minerals. They can significantly oxidize these R2 minerals into R3 minerals, and to generate those R3 silicate-rich short-range ordered minerals. And this kind of minerals, they have much higher specific surface area to combine with organic matters to form the organic matter associations for soil structure formation. And then after that, more and more the plants can grow. For example, the left picture shows the one pot experiment, the larger pot experiments that's showed during the more than 4 months cultivation. These sorghum plants, they can grow in the mountains, and they can even generate some seeds there. That means they can finish their 1 cycle of the living, and furthermore, some kind of nitrogen bacteria, nitrogen fixing bacteria and legume plants, they can associate with each other to finish the nitrogen fixing processes. And this kind of the tolerant plants, their roots are very powerful, and when their roots interact with the minerals, how can what things can happen? So that's why we have used one compartmented cultivation system to mean how the roots can interact with the mountains. We found interestingly more and more the secondary amorphous minerals was generated after the root activities. And those kind of secondary minerals, actually they participated in the occluding of other particles and organic matter into the soil aggregate structure formation. So that's been evidenced by the SEM at the sub-micro scan, and more secondary minerals, they underpin the stability of these soil aggregates. And through the further geochemical analysis, such as the synchro-based X-ray spectroscopy, the more secondary iron and silicate-rich short-range ordered minerals was formed and accumulated. And this kind of secondary mineral sediments were mainly in the size of like 10 to several hundreds of nanometers in diameter. And this kind of minerals, very powerful in the occluding more and more functional microbial-derived organic matter into some small soil aggregates. And furthermore, that means in the mountains, particularly some kind of highly alkaline mountains like the bauxite residue. And we have recently found actually this kind of tolerant plants can actually dramatically decrease the pH of the alkaline conditions of the bauxite residues. And actually, this kind of sodalite minerals was decomposed, and more this R2 and acidic minerals were co-precipitated and on the surface of this residue or this kind of roots. That means these kind of roots were very powerful in the dealkalization and accelerated the alkaline mineral resin and for secondary mineral formation. And then after the roots the powerful roots, more and more soil aggregates were formed. This was evidenced by the more photos that a lot of roots they grabbed this mineral and mineral particles from the tailings to generate some resistant water stable aggregates.
No.
Yeah. And furthermore, more and more, some microbes like some microbes fungi. This kind of microfungi, they can make association with most terrestrial plants, and the advantage of this microbe mycelium was that this kind of mycelium, they have a very fine, even much smaller diameters than those general roots. The general roots has a diameter of nearly more than 100 micrometers, but this kind of mycelium, they only have like 3 or 4 micrometers. And this kind of mycelium, they can penetrate in some fine particles and a fine porosity in the mountains, and they can, accelerate furthermore the mineral resin, and their exudates and their mycelium-derived organic matter can interact with the minerals further. And also this mycelium, they can entangle more and more mineral particles to generate more stable, larger scan and larger micro aggregates to facilitate the functional development of the soil system in the tailings. And more, our recent study found actually after the microrhiza found colonization, and that means the microrhiza and the plants engineered soil technical soils in the tailings, more and more legume plants. These kind of legume plants were they were sensitive to the mine, especially the alkaline and the saline conditions. But after our earlier eco-engineer processes, this kind of legume can grow in the advanced technical soils developed from the tailings. And also there are some nodules can grow there. So the 15 isotopic nitrogen analysis from actually there's some signal of more and more nitrogen fixation function was occurred in the mountains. And this kind of a colonization of the legume and the nitrogen fixing bacteria can furthermore increase the aggregate structure formation, and particularly this kind of nitrogen fixing bacteria together with the legume plants roots, they can further increase the nitrogen rich organic matter stabilization through association with the minerals within the soil aggregates. That means more and more stable, more diverse and more stable microbial-derived nitrogen-rich organic matter can be accumulated in a technical source. So as a take-home message, so our study found that we can use the nature-based solutions, and we can use some extra exogenous organic matter and functional microbes and plants to accelerate the soil formation processes in the tailings. And the background, the basic processes is the key is the mineral resin, the organic mineral association, and the development of soil structure development. In our technical soil study, so we have gone from the port study and to the on-site IBC at 111 meters on-site IBC study, and finally onto the mine site study. So they all going very well, but ongoing we have developed many more, studies in China to develop or to to make this proof of concept of converting tailings into soils into realization to help the more, sustainable management and reclamation of the mine site. So that's also my presentation, and welcome any questions. Thank you so much.
Thank you, Song Ling, for your interesting presentation. Very, very interesting. I want to ask you a question, a curiosity. Have you characterized the microbial communities adapted or stimulated by the addition of organic matter in your test?
Yeah. Thank you, Valerian. Yeah, this is a very important question. Actually, we have used the DNA sequencing work to zoom in the microbial communities, which was published in iScience. So actually, from the beginning, there are a lot of some lesser bacteria, but from after addition of organic matter, there are more and more heterotrophic microbes, including these sulfur oxidation bacteria. They can they can use this kind of organic matter to generate non-energy and also generate some other microbial molecules. So this kind of all things, actually we are now doing some more work, to use some DNA sequencing work to zoom in some virus or some other kinds of macro food web to see how they can develop from the tailings to early technosoil to advanced technosoil with different plants colonization. Yeah. Thank you.
Okay, thank you. In the chat, we don't see any questions, but if someone wants to ask in the second part of the conference.
Valeria, sorry.
Okay, okay.
No, I'm not sure you can see the chat. There are two questions actually in the chat, and I can take that. One is from Dave Cook. Dave is from Scotland, the Mining Rehabilitation Authority from UK, so I think it's a really, really important person. We want them probably to apply some of the techniques that we are showing. Let's say, happy that Dave that you joined. The question from Dave is, how does this process compare with standard hydroseeding, direct application of an artificial growing medium directly to the surface?
Sorry, could you repeat the question?
Sure. How does this process, the mine tailings soilization, compare with the standard hydroseeding, direct application of an artificial growing medium directly to the surface?
Okay, thank you. You mean the artificial medium? Yeah, I think someone use artificial medium, like you use some, even someone use some like topsoil. The one method is topsoil, but there's no topsoil actually in many areas, especially in many China or Australia. The second one is someone use some artificial medium. They can, for example, some vermiculite or some kind of, but this kind of things, they can use some very small area, but for the larger area, is must costful. So it's very hard. So our methods, we use the nature-based solutions, and we only need some organic matter. So from the local area, and we use the organic matter into that to as a kind of initial tools to accelerate the soil formation processes. And this kind of thing is we don't need some extra to spend a lot of money to to get more other artificial materials to use that. It's just it's very costful. So we hopefully in future we can develop a kind of a serious methods. We can use the local conditions, local materials, local microbes, local plants, and local organic matter, to facilitate the directly revegetate the mine site. And that's our goal.
Okay, I think it's a good answer. Dave, we could put in the chat if you are satisfied with the answer. Songlin, there are other couple of statements in the chat, not a directly question, but statement. If you could come back with them and see if you,
thank you.
If you have anything to add to. One is from Akram from Iran, and then another statement from Dave. Okay, Valeria, if you agree, I can present the next speaker.
Okay, Songli, thanks. Can you stop your the share or your?
Okay. Yeah.
Thank you. Thank you.
Oh, thank you.
Okay. So Marco, I present.
Okay.
Present you.
I will present the next one.
Okay.
The next one. Next speaker is Graham Miller from Senversa, Australia. He will present. His presentation is integrated method for assessing the extent and risk posed by soil-led contamination from mining and smelting sites. We know, Graham, that lead is a major concern because we know very well that is very, very dangerous material, for instance, in paintings. And I hope to see some good solution from your presentation. Graham?
Hello, can you hear me okay?
Yeah, we can hear you.
Okay.
And we can see perfectly the slide.
Terrific. Thanks for the introduction, Marco. So yes, my name's Graham Miller. I work for a company called Senversa in Adelaide and Sydney. Thanks for dialing in, attending and listening to my talk. And thanks for the invitation from RemTech and Aquacon Soil. So before I start, I just wanted to acknowledge the fact that Australia is a place that's got a very long history of habitation from Indigenous people, and the work that we do as environmental scientists and engineers in Australia is about restoring some of the degradation that's happened since industrialisation of Australia, and that includes most significantly mining and smelting activities, which form a significant part of Australia's economy. So today I'll be talking about the challenges and problems that we face in investigating mining and smelting sites, and particularly as it relates to soil-led contamination. I'll then talk about some of the methods that we can use to overcome some of those challenges and problems. And obviously I'm talking about lead in this instance, but similar approaches can reasonably be applied to other metals, and also metals and lead in roof dust, which is where airborne emissions from smelters and mines also tend to accumulate in significant amounts. And I guess, as Marco alluded to, I'm specifically talking about lead in this instance because lead is probably one of the most pervasive toxic elements on our planet. It affects and poisons about a third of the world's current childhood population, so about 800 million people, and is attributed to cause about 5 million adult deaths a year, which is more than that caused by HIV or malaria. So it's a significant health issue. And in relation to base mines and smelters, well, they form a key source of lead contamination in the environment. And then lastly, I'm talking about soil because soil forms a key sink and secondary source of exposure to lead contamination. So in terms of the challenges, well, mines and smelters are often very large sites. And if they're large sites, they're going to process an enormous mass of lead. And then furthermore, if they're older operations, they probably operated and occurred when environmental controls were pretty limited or possibly absent. And the consequence of that is there would have been significant fugitive and stack emissions beyond the boundaries of the site over a very long time, sometimes decades, and probably in the case of Europe, having an older mining history, centuries. So it follows, I guess, that soil-led contamination from mines and smelters can be very extensive, can impact on a very large number of properties, both private and public. And particularly at older mining and smelting sites, they're often rimmed or surrounded by residential properties that were originally built for mine workers and smelter workers, but continue to be inhabited even beyond the operating life of those facilities. And whilst we want to definitely go in and sample some of those residential properties that may be affected, because that's probably the setting in which the potential for exposure is greatest, or non-occupational exposure is greatest, we don't want to do that until we have evidence that there's actually contamination at those residential properties, because otherwise we might create unnecessary community concern, anxiety, and start to lose control of the project before we've even started. So that's where a key sort of structured process is vital. And another sort of key challenge of investigating smelter and lead and mine-related lead contamination is that there are other key and again pervasive sources of lead in our environment. And the most common of those is lead-based paint residues, and also the imprint which the use of leaded petrol has imprinted on our general environment. And if our task has been to, or if we've been commissioned to assess the nature and extent of smelter or mine-related contamination, we need to have methods and approaches to be able to discern or discriminate between the contamination that might be associated with the mine and smelter and that which just represents lead contamination associated with the domestic use of lead, being that lead-based paint and leaded petrol. So the overall approach to assessing soil lead contamination from mines and smelters isn't that different to how we assess other chemicals and other sites. However, it requires a bit more careful planning and consideration because of some of those challenges and problems that I discussed on the previous slide. And the first step is really to assess the historical uses of the site, its metallurgical processes, and some key aspects of the environmental setting, which are most likely to affect the distribution and dispersion of mining and smelter-related lead in the surrounding environment. So, for example, we want to determine the mineralogical nature of the ores that were mined or processed at the smelter, and specifically, apart from lead, what are the other major metals or metalloids that are in the ore body? Or are there other unique sort of trace elements that could form an identifier for a source or a contaminant associated with the mine, as opposed to from those other sources that we spoke about? We obviously also want to know where those sources specifically occurred at the particular sites. So whether it's a stack or whether it's a waste pile, those sorts of things. And finally, we need to understand, obviously, the prevailing wind direction. I've got a nice image there showing the direction from a historical area where the emissions from a stack were moving. So I want to know the nature of the material processed or mined, where those activities occurred, and in what direction the emissions from those activities could have taken us. And then from that sort of a culmination and integration of that information, we can start to identify where in the surrounding areas the mine-related or smelter-related lead contamination may exist, its possible mineralogical nature of that smelter-related lead contamination, and other metals that we might expect to see if the contamination is from the smelter. And then we've sort of once we've developed that hypothesis, then the next step is we want to prove that up. And the best way to prove that up is to start sampling in public open space areas. And in those areas that we've determined from that first sort of desktop review process, we think are most likely to be affected by the contamination from the mine or the smelter. The benefit of sampling in public open space, as opposed to just knocking on people's houses, is that it allows us to fairly unobtrusively examine and assess the potential extent of the smelter-related contamination, but also avoid some of the other confounding or contributing sources of lead. So, for example, by sampling in road reserves and those sorts of areas, we can not only identify in background areas, but also in the potentially affected areas. we can consider and understand the contribution from lead from vehicle emissions, as well as those attributed to the mining-related activities. And in those public open space areas, we're unlikely or less likely to find the residues of lead-based paint. So we can start to understand what the chemical signature of mining-related lead is, as opposed to the chemical signature from other potential sources. So just wanted to sort of provide an example, and it's using a copper smelter where we've worked, or I've personally worked for about 20 years. So as part of that first step, that historical review, we established that the smelter over its about 100-year life span processed sulfidic rich ores that were rich in copper, lead and zinc. So they were the primary metals that passed through the smelter. We also established that the key sources of emissions were from a small stack, which for about the first 50 years of its operation didn't have a baghouse. So all the fume and all the particulate matter was discharged from the stack unabated. But the other key source for fugitive emissions was ore and concentrate that was stored uncovered adjacent to the site boundary, again for many decades. And then we also identified the prevailing wind that would have cast those emissions over the surrounding residential areas. So having done that, we then went through the process of doing a sequence of about 1 kilometre long transects of soil sampling in these public open space areas, which we did parallel or sub-parallel to the prevailing wind direction. And what we found was that the concentration of lead in soil was greater than our investigation level for residential kind of land uses, up to about 800 metres or 1 kilometre away from the boundary of the smelter. We also, and that contamination was generally in the upper 0.4 of a metre of a profile, which is consistent with the fact that the source of that contamination was from airborne deposition. And we also found, in just looking at this top figure that I've got there, that we had a very consistent and sympathetic relationship between copper, lead and zinc. So those three primary metals that were in the ore and concentrate that were processed at the smelter. And then when we plotted that on a trilinear or ternary plot, what we saw is that predominantly the lead formed about 40% of the total concentration of copper, lead and zinc when they were all added together. So you can see the vast majority of samples plotted in that lower part of the triangle, but we got some exceptions. For example, that one at the very top that's been identified by that sort of bit of script. And we took that as being a source of lead that was associated with a different non-smelter related source. So from that public open space sampling, we identified the likely extent of contamination, which at that stage incorporated about 400 residential properties, the likely depths at which that contamination might exist, but also the likely chemical signature. So we could use that to discriminate smelt-related lead versus lead-based paints when we started investigating in private properties and where lead-based paints may be more prevalent. It's also worth noting that there are other methods that you can use to identify smelt-related contamination. They include isotopic analysis and speciation. I guess the limiting factor with those is that with so many potentially affected properties and with different confounding sources, it might be impracticable to actually apply those sorts of methods to so many areas and so many samples. And so a more simplistic means of doing that would be looking for chemical signatures that you can readily obtain and identify from standard analysis. And as an example, at this property, for example, the key emissions that would have occurred would have been as lead sulfides, lead sulfates, and lead iron oxides. We collected samples from public open space. We did X-ray absorption spectroscopy and found that most of the smelter-related lead had transformed into lead-sorbed to organic matter, humic matter, and clay particles. So the lead, it had been in the environment for a very long time. It had been subject to weathering, and had transformed. So those alternate forms of identification, being isotopic and speciation analysis, might not always be conclusive in terms of discriminating between smelter or mine lead and other sources of lead. Having established this fairly large, potentially very large area that might be affected by the smelter or the mine, it's important to note that not all, I've put in here, not all lead is created equal. And what I mean by that is that the bioavailability and toxicity posed by soil lead can vary quite significantly, and it's based on a range of different factors. So the literature tells us that the mineralogy of lead, its concentration, the grain size in which it occurs, the soil pH, the clay and organic matter, the phosphorus content, other metal content, so iron, aluminium and magnesium, and a few other factors can affect its bioavailability, so its potential to enter the bloodstream, and therefore its toxicity. So in Australia, for example, our generic guideline values assume a very conservative value or assumption in terms of the bioavailability of lead, which is a reasonable approach because of the different forms of lead that we might be encountering. So where we have a very large area of land that's potentially affected, it follows that we should sort of make every effort that we can to assess what the bioavailability of that lead might be, what its toxicity might be, and then that helps us potentially derive an area-specific value that we can then make some more informed decisions on whether the lead that's present in soil forms a risk or not, and what area that risk may exist in. So you can do that through, and this forms the step 3. So having established the area through the public open space sampling, let's understand the risk that lead poses. You can do the bioavailability testing through animal trials, so in vivo trials, or bioaccessibility tests. Our preference is obviously use the bioaccessibility test because there are clear ethical issues with animal trials. They're very long and expensive, whereas the bioaccessibility tests are in vitro. They're very quick to do. They're relatively inexpensive to do. You can test a lot of samples and then use the data from that and incorporate into blood lead models using, for example, the US CPA IEUBK model to derive an area-specific guideline value. And so that's our step 3. And again, using the same property as an example. So when we first applied our generic guideline value, which is 300 milligrams per kilogram for soil lead, that top image shows the part of the suburb potentially affected by soil lead contamination. However, we then did some SBRC in vitro bioaccessibility testing. And after doing that, we were able to derive an area-specific value of 400 milligrams per kilogram, so 100 milligrams per kilogram higher, and that reflected the fact that the lead in soil was not as bioavailable as assumed in the derivation of the generic guidelines. And what that meant is we went from looking at an area where we had potentially 400 affected houses to now looking at an area where we only had about 70 potentially affected houses. And so obviously a huge cost saving to the program. It also allowed us to really target our engagement program to then only be knocking on the doors of people who were potentially affected, and also being able to explain to people that we weren't investigating the reasons why they weren't part of the testing program. So coming to some conclusions and recommendations, hopefully I've identified that there are many challenges when you're assessing lead-based contamination or soil lead contamination from mining and smelting sites. And those challenges really are principally associated by the scale and potential extent of that contamination. And going with that scale and extent, you're having to deal with many different landholders. And then overlaid on that is the fact that there are other confounding factors like soil lead, like lead-based paint contamination and lead contamination from historical vehicle emissions. However, with careful planning and staging the investigations, we can try to overcome those challenges by identifying specific markers for lead, using bioaccessibility to derive guideline values which are reflective of the risk, and therefore really targeting the areas that require assessment and potential management. And look, the literature is full of excellent and unfortunate examples of mining and smelter-related contamination. I've listed a few there that appear most often. There are obviously many others in Australia. Broken Hill, Port Pirie and Bullaroo are some significant ones. I won't attempt to pronounce the French ones, but there's a couple of good examples there, as well as Romania. So I encourage you to go and have a look at those if you've got a particular interest. And I think that's about it. So I'm happy to take any questions, or unfortunately I won't be here at the end, but if you have any questions, feel free to email me. Thank you.
Thank you very much, Graham. Very, very interesting presentation. We have a couple of questions from the chat. First one is from Christy. So Australia to Australia. And the question is related to the background. How do you account for elevated background concentration of metals where smelters are located in close proximity to a mineral resource? So how do you manage, let's say, natural background and anthropogenic background?
Well, I guess that's particularly difficult at a mining site where you might have gossans that are close to the surface. And in Australia, that isn't defined as contamination because it's a naturally occurring existence or a naturally occurring situation. But ideally, when you're looking for a background location, you're looking for a similar setting where you have similar potentially confounding factors, but where you don't have the contribution from that key source that you're looking at. So in the case of Broken Hill, that's quite difficult. But in some ways, you'll see that through the soil profiles. So the residual soils may not be enriched in the metals that exist at depth in the rock, but may be enriched from the emissions that occurred from the mining and smelting activities. So it's not easy, but again, that's where a careful background review is important to identify where there may be local mineralisation, and then identifying your background areas where there may not be.
Thank you very much, Graham. Second question is from Dave Cook from the Mining Rehabilitation Authority of the United Kingdom. And the question is the use of microtox or similar microorganism-based tests that don't need higher animals, quicker and cheaper than leachate speciation and bespoke availability tests. Do you have considered the possibility of those tests?
Well, in Australia, guidance makes provision for allowing modifications to our guideline values by either doing the in vivo trial or using 3 different validated in vitro bioaccessibility tests. So the SBRC one is one, PBET is the other. I can't remember the third. We use the SBRC because it's probably the easiest. It generally produces the most conservative results because you use quite a low pH, and we use the gastric test. So it's only validated to the gastric phase, not the intestinal phase. And again, that provides some conservatism because lead is absorbed in the intestinal tract as opposed to the gastric form. So in the gastric part of your body, the pH is 1.5 to 4, so you get a lot of dissolution. As that passes into your intestinal tract, the pH is about 7. So a lot of the lead that might have come into solution might reprecipitate and then be passed through your body. So by using a gastric bioaccessibility test, you're still providing some conservatism in your estimates.
Good day. Thank you, Graham. There is a last question you partially answered is from Biji. I think he or she's from China. And this remind me when I made some test in acid mine drainage in China with the pH2. It was unbelievable to me. It was the first time that I deal with the acid mine drainage. And the question is, what about the pH of the soil? Well, you already answered to 1.5 to 4. And the second question is, if the lead contaminated area has high sulfate concentration too, and eventually, probably not said, but how do you manage eventually sulfate concentration as well?
Well, inevitably, there probably will be high sulfate because most of the lead contamination comes from galena, which is a lead sulfide. And so particularly at smelter sites, the most significant emissions during operation are sulfuric or sulfur dioxide. So there will be quite a bit of sulfate in the environment. In terms of potential health effects posed by sulfate in soil, I suspect they're pretty minor. They may produce things like corrosion of structures and that sort of aesthetic impact. They might also support the formation of anglesite, I think it is. It's a lead sulfate, which has a lower bioaccessibility than, say, other forms of lead. But in terms of managing risks to health, sulfate is really probably a pretty minor issue.
Okay, thank you very much, Graham. Graham cannot stand up to the final discussion panel. I think could stay just a few minutes. If you have some last question, please do it in the chat. Maybe Graham can take some minutes to answer to any curiosity that you may have. Thank you very much, Graham, for your time and to share your knowledge in this webinar. Thank you very much.
Thanks for having me.
Handing over now to Fred for presenting the next speaker. Let me, now that we are the right number of people present, let me remind also that this is a session organized by RemTech Europe and Aqua Consol. Is a pre-event of our two main events. Aqua Consol will be from 16 to 12. From 16 to 20 of June 2025 in Liège, in Belgium. There is a still place if you want to join. RemTech Europe will be in September, 15 to 19 of September. Please take information on our website if you want to know more about this. We will put maybe some more information in the chat. Fred, I hand over to you for presenting the next speaker.
Thank you, Marco. It's a pleasure to welcome Diego Barragano from the Istituto di Scienza Tecnologica del Carbono, and moving from the risk assessment with lead now back to some phytoremediation of soil polluted with mining area, and specifically looking at the use of nanoscale zero valent. So Diego, over to you.
Just give me 1 second because I'm trying to connect the camera. Okay. I think that you can see me now, I hope. And we'll try to share the screen.
Yes, we can see you.
Okay, so I will share the screen. Okay. Can you see my screen?
Yeah, we're all good. Thank you.
Thank you so much for the introduction. So today I'm going to speak about the phytoremediation of polluted soils by combination of nanoscale cerebellum iron in case of mining areas. So this work was developed in the geological Spanish Geological Survey in collaboration with the University of Oviedo. No, it's not. No. So first, I would like to talk about the soil amendments that are used for soil remediation. The application of the amendments try to apply different materials based on organic compounds or inorganic compounds, trying to mobilize or immobilize the pollutants into the soil. So from our approach, we are trying to decrease the mobility of the potentially toxic elements that are found in mining areas to be immobilized to avoid the phytostructure with the plants. So we are trying to develop the phytostabilization of the soil. So inside of these different type of materials that can be used for this approach, we are working a lot using nanoscale zero-valent iron nanoparticles. So this type of amendment is inside one big group, the iron-based amendments, that try to simulate the iron oxide phases that are already presented in the soils naturally. So we synthesize the zero-valent iron core with a size of around 15 nanometers with a shell of different iron hydroxide shell. So once that we have this structure, it's allowing different pollutants immobilization due to this configuration. So the oxidation of the zero-valent iron can help in the mobilization of some metals, and also the iron oxides can capture by absorption these metals and metalloids onto the surface. So we are creating new iron oxide phases in the soil after the application of the nano iron and the consequently oxidation of them. And how we are able to combine the nanoparticles with the phytoextraction, with the phytoremediation. So in an untreated soil, we have our plant, which is able to uptake some part of the pollutants to be in the root system or to be translocated to the aerial part, to the leaves. When we are applying some nanoparticles, nanomaterials to immobilize the pollutants into the soil, the plant is not able to uptake these metals. And the problematic in this case is that these plants can also reveal some problematics because of the point of view of the nutrients, because some nutrients can be also immobilized in the soil, as it happens with the phosphorus. And we have also other possibility, which is named nanophytoextraction, in which we are applying nanoparticles to the soil to increase the mobility of the pollutants, of the PTEs, and to be promoted to be uptake by the plants and translocated to the air part. In that case, we are doing some experiments with graphene oxide nanoparticles. We are promoting the mobilization of arsenic, and the plants are able to uptake more amount of arsenic into the leaves. But in this case, we are thinking in other possibility that it's what's happening with the nanoparticles translocation. If these nanomaterials that we are applying to the soil can be also uptake by the plants or not. So in this context, we apply our technology with the nano iron and the birch plant for phytoremediation in the mercury mining area located in North Spain. This region is one of the biggest mercury mining areas in Spain after Almadén in Ciudad Real. This is the old mercury mining area because all the mercury mines were closed in the 70s, and now these sites were abandoned without remediation. So we have plenty experience on these sites, not only on remediation, but also on characterization. So we were performing some experiments to evaluate which is the degree of the pollution, which is the areas that are heavily affected by this type of pollution by arsenic and mercury, but also using drones with remote sensing. And we were developing different amendments, coupling that with phytoremediation. So I will present one pilot experiment that we performed in the Terronal mine. This mine was closed in the 70s without restoration and no waste management. And we detected soil affection by arsenic and mercury because the arsenic was also in the mineral paragenesis. So when they were roasting the mineral, the ore, the mercury and the arsenic were released to the environment, and some waste disposal was performed without any control. So we detected concentrations of arsenic higher than 4% in the soil, and also concentrations for mercury higher above of 2,000 milligrams per kilo. So this is the first application of nano iron in soils reported in the literature under field conditions. It was already applied for groundwater treatment, but not for soils. And after the application of the nano iron by mixing a 1% dose of these nanoparticles, we observed that after 72 hours, the concentrations of the availability of arsenic and mercury using the TCLP test were decreased a lot. 74% of decrease for arsenic and 86% of decrease for mercury. So we were monitoring this experiment for 32 months, and it was, the leaching of the arsenic and mercury remains equal, but we were thinking what's happening in the real long term. So we come back to the site 6 years later, and we observe the similar results. We performed the arsenic and mercury leaching using TCLP, and the results were the same. So we know that this application of nanoiron is stable a long time, but we were thinking what's happening with the nanoparticles after time, if they are oxidizing or not. So according to the literature, after 15 months, all the nanoiron, the cerovalent iron, should disappear because of the oxidation. So we performed some analysis in Soleil synchrotron and the cipher that the iron speciation was linked to ferriterite and goethite lipid oxide. So we didn't identify cerovalent iron, at least in the bulk samples. So regarding the mercury, we performed thermal desorption, programmed thermal desorption to identify the mercury phases that are presented in the control soil without nanoiron and also in the treated soil. And we identify the same species. We identify sulfur, cinnabar, metacinnabar, and also mercury bound to goethite, to iron oxides. But we were not very sure about the quantitative method of the thermal desorption. So we went to ALBA synchrotron, we performed X-ray absorption spectroscopy, and using the linear combination fit, using the same patterns, we estimate the same phases that we already know, cinnabar, metacinnabar, and mercury bound to goethite. But it was possible to do a quantitative analysis and identify the mercury bound to the goethite was increased. So our hypothesis is that the mercury is bound to the new iron oxide phases that we are creating with the nanoiron. And what's happening with the arsenic? We identified that mainly the arsenic species presented in the soil was arsenic 5, arsenate. And even after the application of the nanoiron, we identified the same species, but it happens in the bulk sample. So we went through the microscale to see what's happening. We prepare the soil embedded in resin. We prepare these peculiar forms of the probe to be adapted to the beamline nanoscopium in Soleil. And we perform XRF mapping on these soils. So we were focusing on the mapping of iron, arsenic, and mercury. We identified these different type of particles. And in the case of the polluted soils, all the particles that were iron-bearing particles reveal the arsenic speciation of arsenic 5, mainly on the surface of these particles. So we know that if we are identifying iron oxide phases naturally found in the soil, they have arsenic 5 only. But then we found that some of the particles reveal arsenic 3 concentration onto the surface. So in these particles with arsenic 5, not presence of iron 0 was found, only iron oxides. But in the case of these iron particles with arsenic 3, as it is shown now in the graph, we have found particles with 50% of arsenic 3 onto the surface of the iron oxides phases, corresponds with iron oxides onto the shell, but we detected the core with cerovalent iron. So this concentration of cerovalent iron in the soil, it's very few, so it was not possible to detect it in the bulk analysis. But if we are looking for the microscale, we can identify the same structure of the nanoparticles, but a bigger scale. So our hypothesis is that the nanoiron, the nanoparticles, are agglomerating the soil. So we are creating new microparticles with a core of cerovalent iron and different iron oxides around, and the arsenic 5 is attached source onto the iron oxide phases, but also the arsenic 5 is reduced to arsenic 3 by the oxidation of the nanoparticles, but the arsenic 3, it's also bound to the new iron oxide phases. So this is the mechanism. Somehow the arsenic is immobilized into the soil. But what's happening with the plants, the interaction with our plants for phytoremediation? So we moved to the subterranean mine, which is other mine close to the site. Here the soil affection is less. We have concentrations of 9,000 milligrams per kilo of arsenic and less than 1,000 milligrams per kilo of mercury. And we apply the nanoparticles and also use Betula pubescens, the birch plant, for phytoremediation. So we prepare some plots applying the nanoparticles, and we use these birch plants. We test first at the beginning at the lab conditions. So I will present first these results. And what we observed by combining nanoparticles also with compost, because in this soil we were in the dump and no organic matter was there, so it was necessary to apply organic matter and some nutrients for the plant. We were a bit surprised that the plants growing in the compost died because of the mobilization of the arsenic. This compost has a phosphorus inside, so these phosphorus are in competition with arsenic. The arsenic is mobilized, and the plant was not able to uptake arsenic. So the plant died because of an excess of the accumulation of the arsenic in the plant. But when we are applying the nano iron, this arsenic was immobilized and the plant was able to develop better with a better growth ratio and also with less accumulation of arsenic on the leaves. But if we are comparing the dose of the nano iron, that in this case we apply 1% and 2%, we observe that the roots development system was bigger in the case of higher dose of nano iron. However, if we are taking into account also the economically point of view, we selected 1% dose to be applied in this mine. As you can see, this soil is not really a soil, it's a techno soil with a big amount of different wastes and slags mixed with the soil. So when we apply the nanoparticles, were not differences on the aerial biomass that were collected, but just on the accumulation of arsenic and mercury. So the plants that were growing in this plot with the nanoparticles treatment were accumulating less amount of arsenic and mercury. And if we are looking for the roots, we are pending or receive some microbial analysis of the soil of the rhizosphere. But as you can see in the picture, the structure of the roots were better developed with some indices of microbial activity. And also the root system was better developed in the case of the control. So now we are trying to decipher which is the effect of the plant on the arsenic mobility in the soil. So my PhD student, Salvador, is now in Nantes University in France, trying to use rhizobox with the birch plant to extract the pore water from the soil. So we are using some gels to extract the pore water, and now we are using the hyperspectral camera to map the gel in order to know the arsenic speciation distribution in the pore water, not in the soils, trying to evaluate the effect of their plants into the soil, not the soil into the plant as we were doing until now. So as final conclusions, under our experience, we know that the field application of nano iron in soils, it's a success, it's feasible, and also in combination with phytoremediation, because we need to combine different techniques to make the restoration of mining areas. It's not enough with the application of amendments. We need to use different plants to restore the areas. And from the point of view of the economic cost, the nano iron application can be a limiting factor, but in the case of extremely high pollution and in the case of these mercury mining areas, it's not a limiting factor. And the effects of the nanoparticles in plants is a synergy, so it's a promising approach for mining restoration. So thank you so much. I would like also to acknowledge all the collaborators for these projects and also the project fundings. So thank you so much.
Thank you very much, Igor, for this presentation. Great to see some field application also potential and the use on NZVI. And I was having effectively a question about the cost if you are going for large area and using NZVI. But as you pointed out, if it's a quite area with high pollution or issues of environmental pollution, it's not such a limitation. But nevertheless, are you considering to look at something different that instead of using the NZVI to look at, there is quite a lot of broad research now looking on more low-cost alternative. And I'm just wondering if this is something you will be looking into.
Yes, absolutely. We have tried and we are starting with some experiments under field conditions using cerebral iron microparticles. So the cost of using microparticles is 10 times less than using nanoparticles. So we are doing comparisons on the microscale versus the microscale. And in some cases, is similar results, no so much difference. Some cases, the nanoparticles, this nanoscale, it's helping to be more reactive and more fast. It's faster results. but in the long term, we have similar results. So in our opinion, we can use microparticles, and we synthesize microparticles of soluble iron, but we are trying to reduce some slags coming from the steel-making industry that we have in our region, trying to create these iron-based amendments more economically. But in this case of mining areas, that we need also nutrients and organic matter to restore the soil, not from the point of view of remediation, but also for the soil health. We are trying to combine different amendments, not to apply a techno soil or artificial soil, but to combine different amendments with the natural contaminated soil. So we are applying sludge compost. We are using also a sludge biochar, hydrochar in combination with these microparticles of soluble iron and still making slags, and also we are using other byproducts coming from other mines. We have magnesite and dunite byproducts coming from this type of mining areas that we are collecting the residue from the industrial plants, and because of the granulometry, or they have not good quality for other application in the ceramic industry, we are using this as an amendment for soils, because we can use this for increasing the pH. So it's a balance of different amendments to correct different parts of the soil parameters.
Yes. And yeah, if you have in the attendance, if you have questions, I don't see them yet on the chat, but for now, so obviously it's an idea to improve the viability or bioaccessibility of this metal to be uptaken. So are you also considering to look at different type of plant for biomass and then energy recovery and recovering the metal later on in the ash? Is that the full cycle, and what sort of plants might be or good phytoaccumulator or relevant in Spain, and you could see a wider potential for the region?
Yeah, this is a very good question. We are using birch plant because this is a native plant in the region. This plant is growing very well in the altitude where the mines are found, but we are using other type of plants. For example, in some cases, we are using hyperaccumulator plants that we detected in other mining areas. So we are working now in lead zinc mining area where we detected different hyperaccumulator plants. We have Nokaya plant. We have also some Brassicacia plants that we are using for phytoextraction. So we have one project now trying to extract the contaminants to the aerial part using these hyperaccumulator plants. Then we are collecting the aerial part, and we are doing biochar, trying to use this biochar as amendment in different cycles. So we are taking into account what's happening with the metals when it's in the biochar, because we have the metals in the aerial part. So after the pyrolysis, we are concentrating these metals, but these metals are immobilized. So if we are applying this biochar with presence of metalloids, it's not a problem if we are applying to very contaminated soils where the concentration is extremely high. So we are trying to make some cycles reducing this type of plants, but we are working always with autochthonous plants, trying to reduce the plants that we know that are able to grow in the site.
Okay, yeah, that's we had a question from Belgium, from Cécile Nouet. She was asking about native plants, so which you are covering. She was also interested to know whether you are looking at trees or trying to combine some area with trees and other more herbaceous or different plant type. And do you see like as a phyto management strategy for the long term in that region?
Yes. In case that we are interested on focus on the understanding of the mechanisms, we are using only trees, as it happens in the results that I show. But we are performing some experiments for restoration in mining areas, and we apply the amendments, and then we are using herbaceous plants like Lolium perenne and Agrostis capillaris, trying to have first step of phyto management using this raygrass, using these herbaceous plants, and then we are using the birch plants after that. So we are trying to do in different steps for the mining restoration. But in that case, it's hard to us to understand the mechanisms in which the plants are uptaking the plants, because the different types of plants are competing between them. So when we want to understand what's happening, we are using only one, but we are focusing on the restoration in working with companies. We are doing in different steps by mixing different types of plants. Okay, so it's still more work to do and effectively finding the synergy where possible. And thank you very much for that great talk and for the question in the audience. And now I will pass over to Valeria. Thank you so much. Thank you.
Diego, can I ask you a curiosity?
Yes.
Sorry. I performed a phytoremediation study with nanoparticles of titanium oxide with polluted soils, with polychlorinated biphenyls, and also with heavy metals such as lead, zinc, and vanadium. We noted that our nanoparticles, nanomaterials, caused a very low development of the root system, but contributes to promote the reduction of contaminants. I noted that in your case, nanoparticles on zero-valent iron promoted a very growth of root system that sure improve the root exudation. So I was very interested from the study of rhizobox that you will perform, because in this controlled system you can identify and quantify also the main exudate that are responsible of the interaction microbial and the plants. So I want also to know if you can say the microbial investigation you will perform to
Yes, thank you for your question. Regarding your situation, I have some experience with titanium dioxide, but we are using these nanoparticles for demobilization of pollutants, but also for the compactation. Because in one mine, they were interested on create the roads for the trucks, so they need to compact the soil. So they were using titanium dioxide nanoparticles for compaction, but it works also for the remediation because it was immobilizing the pollutants, so the runoff water were not leaching. So maybe the case that the roots were not able to develop, it's because of physical properties of the soil, not for chemical properties. It happens also with nanoiron, that where they are oxidizing, they are also compacting the soil. And in some cases, the roots are not able to develop. So after the application of the nanoiron, after 2 or 3 days, we are using to do manual mixing of the soil to destroy the layer of the nanoiron that it's compacted. So we are airing the soil, and it's better to wait for a week until using the plant. So we are like breaking the soil to break this physical structure that is compacted, and it's helping the plants to grow. So we are doing in these 2 steps because of that. And regarding the rice box, it's ideal to show the effects of the development of the growth of the roots. And for the microbial analysis, I'm not the expert, but if you want, I can send you an email later with all the information, because my colleagues for microbiology are using typically ARISA method using PCR to see the change quickly, the change on the soil microbiology. But then there are all the complete sequences of the sequence to know all the bacteria. But sorry, I'm not the expert on that, so I cannot give you more information now. But if you are interested, I will write my email on the chat. So if anyone have any question, can ask me.
Thank you. Let's move with the next presentation, next speaker. Okay. I pass okay, Teresa Valente is now. Okay, Teresa. Your contribution is entitled From Legacy to Resilience, Environmental Protection in the Face of Mining Contamination. You can start.
Thank you very much. Good morning to everyone. So I will start to share. Okay. Is everything okay?
Is okay. You can move in the wide screen. Perfect. Okay.
It's already in full screen, right?
Okay.
Okay, thank you. Well, so let's start, or let's continue talking about mining, and especially we will talk about old mines in the Iberian Peninsula. So when Romans came to the Iberian Peninsula, they mined gold. Well, today we mine problems. So we have this legacy left behind by centuries of mining. And nowadays we need to discuss how we are stepping up to meet the Europeans' need with strategies for environmental protection in this degraded land. So the challenges that we are faced today, they goes far beyond abandoned mines or just toxic tailings. We are now dealing with the legacy of contamination that's being continuing, reactivated by a changing climate. We have rising temperatures, intense rainfall events, or on the contrary, water scarcity events, and all of which stir up old pollutants in new and unpredictable ways. So this talk from legacy to resilience, environmental protection in the face of mining contamination is really about one thing: how we can transform these forgotten sites from environmental burdens, that's what they are, into blueprints for resilience. And as we go back on the long history of mining in the Iberian Peninsula, well, in fact, this is applied to all Europe, we find more than just records or statistics. The marks remain on the landscape, and some of the traces have been preserved and give us a sense of pride, a sense of identity. They are historic mining sites that help to tell the story of those that lived and worked there. So these places, they become part of our culture heritage, and they are even in some cases part of geotouristic routes. Well, unfortunately, many other remains are less romantic. We have crumbling structures. We have modified landforms that still pose environmental, technical, and even ethical challenges. We know that we have unsustainable extraction techniques combined with the absence of effective regulations. It was like that in the past. And these have led to extensive contamination. The case of São Domingos mine, which is this image that we have here in the screen, exemplifies this challenge. It was once a significant site for copper and sulfur extraction, but now the area exhibits widespread ecological degradation. We have abandoned infrastructures, massive waste deposits. We have acidified surface waters, which highlight the environmental costs of the legacy of mining operations. I remember that a few moments ago, Marco was talking about acid mine drainage with pH of 2. Here in São Domingos, we have negative pH values. So it's really an important issue regarding the contamination and the quality of the aquatic ecosystem mainly. Well, furthermore, many post-mining landscapes here in Iberian Peninsula they include pit lakes that were formed in former open-cut mines. These mining lakes act like long-term pollution reservoirs. They are often stratified and prone to releasing toxic elements into the surrounding ecosystem. And of course, this is posing key issues that include geotechnical stability problems, the problem of containment of contaminants, and very important, the need for complex remediation systems for remediation. We need to make this effort to remediate some of the waters, not in this case of this image where we have pH around 1, between 1 and 2, which is really very complicated. But anyway, we have problems of water scarcity, and we have great amounts of, great volumes of very contaminated water in this territory. So indeed, this is a special pressing problem in the southern Europe, where we have climate change intensifying already existing vulnerabilities. So these shifts in climate indeed has other consequences. We have typical scenarios of degradation related with this legacy, like proeminent erosive features and stable landforms. We have here some images that illustrate these deep ravines, vertical escarpments, fragile sedimentary exposures, and all these represent risks of landslides, surface runoff, and waste transport, particularly during extreme events of rain. This damage has left not only marks on the environment, but also a social, cultural, and even an emotional trail that contributes to the instinctive rejection we currently have when we face the prospect of any mining project. And this is a big problem in Portugal, and I believe in the entire Europe, when the communities reject mining industry, and at the same time we are needing for critical raw materials. So while the past left us this terrible or heavy legacy of environmental damage, it also taught us something very important, that when we look forward, it is clear that mining is not a relic of the past. It is deeply embedded in our future. We still need mining. We will still continuing needing mining in the future. And this chart makes it very clear. We can see here that modern technology, and I remember that Valerio talked about this in the beginning, our technological evolution is driving an ever-growing demand for raw materials. So from these simple windmills, passing to the Industrial Revolution, and now in this cutting-edge technology of the 21st century, we realize that we are needing much more resources, and especially also much more diversified resources. Well, indeed, the intensity and diversity of metals used in our today products have, well, I would say, skyrocketed. And driven by this European Green Deal and the Paris Agreement, we have to take this in consideration. We are here with this dilemma. We need to continue to explore. We need to continue to exploit, but in a responsibly way. And in fact, this mineral exploitation is not just an economic necessity. I believe it's really an imperative strategy for Europe. And these resources that have become essential for sustainable technologies, placing mining once again in the heart of environmental discussions. And we have to deal with this. We are now needing for materials like lithium, like cobalt, like graphite, that were not needed, at least in such a quantity like nowadays in the past. But today they play a critical role in the manufacturing of batteries, wind turbines, and solar panels, like Valerio was talking about, all the European electrification and mobility and ecological transition are needing for these critical materials. So this growing for minerals intersects with the critical challenges of water management. This is another key issue. Water is an unavoidable issue in mining. It's one of the primary sources of concern at all stages of the extractive process. First of all, mining is an industry strongly or with a very intensive consumption of water. And of course, from this results numerous problems associated with contamination of water and water management in general. In environmental terms, I would say that the most critical problems become even more significant when mines are closed down. And the aquatic system, the rivers, the lakes, or even the small streams are the reservoirs or the environmental reservoirs where contamination is most evident and challenging. And one of the most critical and persistent issues is acid mine drainage, as was talking Marco before. Acid mine drainage occurs when the sulfide minerals are exposed to water and air. It's not a simple process like it looks here. It's composed by several complex phases, but well, in a very simple way, we have, as a result of acid mine drainage, an acidic runoff that mobilize toxic metals, also sulfate, of course, which can severely impact surrounding ecosystems and water quality. And mitigating acid mine drainage is technically very complex. And of course, it's also very financially burdensome and often require continuous management and monitoring. It's one of the biggest problems in mining industry and the most, I would say, the most complex to deal with. So this critical nature of water is even more acute when we are talking about scenarios that are facing scarcity. And this is the case exactly of the Southern Europe and of Iberian Pirate Belt and many other mining regions around the world where it is becoming increasingly complex to assure quality supply especially supply of water with quality if you are in semi-arid conditions like we have here in the Iberian Peninsula belt. So from north to south, from east to west, we have our river systems with visible scars of this past mining. We have wonderful, at least I believe that they are wonderful color, but at the same time they are alarming. These red, green, orange use of contaminated streams highlight the extreme ecological stress caused by acid mine drainage, signaling widespread environmental degradation. In these sites, we have physicochemical, ecological, like the algae, and also mineralogical indicators of extreme contamination. We are talking here of pH values often negative, below 2, with only acidophilic organisms like bacteria, eukaryote or not, and this wonderful algae, but they only live here because the environmental is so extreme. So all these colors that I consider real.
Aspetta, faccio la foto.
So, well, these colors, indeed, they are alarming because they represent a big problem. Well, just a small detail of some biogeochemical process that occur in these sites related with the presence of specific organisms. But, well, if you need to efficiently manage water and water is a critical problem here, not only for environmental sustainability, but also for the long-term viability of the mining industry, because, as we said before, we still need mining. Solutions such as water reuse, improvement, treatment, technology, and waste disposal are essential, especially because we are facing uncertainty scenarios in these regions like or water scarcity or very extreme rainfall events. So faced with this legacy, and also, of course, guided by the legislation, the rehabilitation strategies have focused on 3 main types of intervention. Securing old mining infrastructure, such as closed galleries to ensure safety, sealing and isolating reactive mining waste to prevent exposure to air and water and thereby reducing acid mine drainage potential, and improving water management through drainage control in the underground mines and to assure mine water treatment and drainage systems that work efficiently in surface and also underground mines. So regarding treatment or treatments in general, well, there are 2 main strategies that are adopted to address contamination from mining activities. We have the passive and the active systems. Each has its role depending on site conditions, on pollution levels, and long-term management sites. Passive treatment systems rely on natural processes to treat contaminated water. They often use wetlands, which are biological processes. Usually they are combined with physicochemical processes like the use of limestone drains or anaerobic bioreactors. These systems, well, they are low cost and sustainable in the long run, but are typically more effective in sites with moderate or stable contamination levels. On the other side, the active treatment system involve continuous input, human and technological input, including chemicals, pH correction, oxidation, precipitation process, and so on. They are capable of handling higher contamination loads and providing more immediate results, but they require energy, they require infrastructure and ongoing operational monitoring costs. In many rehabilitation projects, a combination of both approaches is usually appropriate or even most effective, with passive systems used for long-term stability and active system assuring quick mitigation where contamination is more severe or complex to deal with. So concerning these treatments that we are using in the Iberian Peninsula, specifically in the Iberian Pirate Belt in the south of Portugal and Spain, most of the approaches have been passive solutions considering the abandonment conditions, we are dealing with legacy, so we need to spend the least amount of money possible. So because we need to deal with the costs of maintenance, most of the times in very remote places. So we also, of course, have some active treatments. Some active treatments. But, well, for example, in Portugal, most of them are restricted to radioactive mines. Of course, we have to consider all the conditions like the contamination loads, the flow, the characteristics of the waters. But we are talking about spend lots of money. Of course, in special places where contamination is really high and affecting human health and ecosystems, we need to use these active systems, and we are doing mainly, as I said, in these radioactive mines. We have here some examples, but I will pass.
Teresa, sorry, could you go to the conclusion because we are running out of time?
Just on the conclusions, well, we have here some examples of the biggest rehabilitation project in Portugal, the Urgeiriça mine, where we have a combination of passive and active treatments. Well, the results are very good and they are complying with the regulation. We have just some problems with manganese, which is very common in these places. Well, I have here this small video that I will pass. Just this, as we are arriving to the end, this message that the mining legacies are complex, but well, we have tools to deal with them and they are not irreversible. We can deal with some tools to solve the problems. I would not pass this. Sorry, I will not pass this video, but I invite all of you, if possible. We have a big conference in Portugal related with mine water treatment and mine water issues, which is the International Mine Water 2025. It will occur in University of Minho. Is a organization with the University of Oviedo. It will held in July from 6 to 11 July. So we were very welcome to discuss mine water issues with examples from all over the world. Thank you very much for the session and to all of you for your attention.
Thank you, Teresa.
Valeria. Okay.
Marco, want to say something? You?
No, I think there are no questions from the chat. Just one on the acid mine drainage that was answered by Teresa during her presentation. I was also curious because I learned today that there is a pH that is negative. And yeah, really, it should be really very, very acidic. I think so. No, so yeah, good to know. Teresa, if you could stay also for the final panel discussion. We have now other two speakers. So one will introduced by me, and the next from Fred. Next speaker is Cécile Nouet, University of Liège. Also, he's also part of the organizing committee of the next Aquacon Soil, and very long CV. I will make it short. She will present phytomanagement solution for economic, social, and environmental benefits. So we go into the sustainability issues. Cécile, floor is yours.
Thank you, Marco. Can you hear me well?
Yeah, we can hear you. If you could share your screen.
Yeah, I will share my screen. Is it okay?
Is it perfect? Go forward.
Okay. So, hello everybody. My name is Cécile Noué. I'm a plant biologist at the University of Liège, and also coordinator of the Waste to Bio initiative. I will say a few words about it just after this. And then I have a special interest on participatory research and stakeholder engagement. I thank Marco and Fred and Valeria for organizing this international webinar and for inviting me to this very interesting topic. So first, I want to say a few words about this initiative that is supported by the Walloon region in Belgium. So it's an ecosystem of different actors in the Walloon region that bring together to promote phytomanagement solution and I would say accelerate the reconversion of brownfield and mining sites. So now we are 130 actors from landowner to universities, service providers, citizens and farmers. And I will present during my talk, I will present a few case studies from Wallonia, but not only, because the goal of my talk is to do like an overview of what is phytomanagement. I apologize because there will be some redundancy with what have been said before because there was already several talk on phytoremediation. So first, I would like to highlight the importance of combining physical, chemical, and biological methods to restore not only mining site but contaminated sites. I see in some workshop or conference, I see sometimes that the different methods are opposed, and I think it's not the good strategy if we want to reach or to restore soil. We need to combine and to find a way to combine the methods and if we want to have the ecosystem services that are delivered by soil restore, I think it's the only way to reach this goal. So phytoremediation, as you know, it's a use of plant species associated with soil microbes and also different types of amendment to degrade or immobilize or extract organic or metallic pollutants. It's the main, I would say, phytoremediation is mainly used as a general term to name this nature-based solution. But a few years ago emerged a new concept that is called phytomanagement. And the idea of this new strategy, but it's not exactly new, but that the phytomanagement not only take into account the remediation of the pollution, but also other benefits delivered by the plant and soil microbes and amendments. So the idea behind phytomanagement is that by using plants, you not only stabilize, degrade, and extract the pollutant, but improve the soil quality, the soil structure, the soil biodiversity, you preserve water resources, prevent erosion, improve carbon storage, meaning that you impact positively the environment, by managing the risk linked to pollution, by increasing biodiversity not only in the soil but also above ground, by also preventing flood, but also contributing to the climate regulation. But by also by covering the contaminated site with a green cover, then you also impact positively the quality of life and the well-being of the citizen, for example, by installing a landscape, a nice landscape, or with the development of parks or recreational areas. And finally, another important aspect of phytomanagement is the possibility to valorize the biomass produced by some plant species to produce materials or renewables energy, and therefore to produce revenues from the phytomanagement solution. Of course, phytoremediation and phytomanagement solution face some challenges. First, you cannot develop phytomanagement solution in any of the mining or contaminated sites. It's really obvious that you have to take into account the future use, land use of the site, and also the land value and I would say the risk that is associated with the pollution. So each phytoremediation and phytomanagement solution is site specific. So it means that you have first to design a redevelopment plan with a detailed strategy of the site preparation, the selection of the plant species and microorganisms. Often you have to do preliminary tests in greenhouse. You have to take into account the time requirement for the solution you plan to implement, and there is also the stakeholders, all stakeholders that are associated to the site are essential to make sure that your plan is actually implemented. So there is a lot of stakeholders engagement that needs to be done. And then, of course, depending on the contamination types, the depth, the mix of the presence of a mixture of contaminants, you will not apply, you will apply different solutions, different plant species. And also there are some other aspects like water access. So often the phytoremediation and phyto solution are proposed for low risk and low redevelopment on low redevelopment pressure area. But it's also possible to envisage this kind of solution as temporary solution on high risk and low redevelopment pressure land. So I will give an example. So there are some current work on developing a business model for phytomanagement. So I give an example here from the Islander project. In this EU project that is ongoing, they are performing a cost-benefit analysis of phytomanagement solution. and you see on this diagram that they listed a series of benefits, but also costs. And the challenge now is, of course, to quantify all these benefits and costs. So, we at the Walloon region, we are also performing this kind of exercise, and we are developing what we call regenerative business model that I hope to be able to present in a future webinar. Then I wanted to follow up with a series of case study, and first because this webinar is held in Taranto city. I've been doing some literature review on Taranto city, and I found a very interesting case study that is called urban forest, and it's what was interesting for me is that in that case study they don't use the term phytoremediation or phytomanagement, but they use the term phytobonification. But it's the same. It's the use of plant and microorganisms to transform brownfield or contaminated industrial site into a green area, and you have a picture of this. The master plan for this, the redevelopment of this urban forest in the city of Taranto. And then there is also this case study about in Taranto and in its region that now farmers for a few years already are growing hemp on agricultural land that are contaminated by industrial activity, former steel industry that closed, I think, a few years ago in Taranto, and they decided that they wanted to change the crop, and they move to hemp production in order to restore the soil health and to stabilize the pollutants that are present in their soil, but also to produce material for construction, but also for textile industry. So I found it was a quite interesting case study from Taranto. And then I will move to a case study in Wallonia that have been developed since a few years ago. The first one, it's a former zinc production site that was turned, I think it was, 12 years ago into a natural reserve. And the goal of this natural reserve is to preserve the flora that is typical from former mining site contaminated with lead, cadmium, and zinc. So it's open to the public and to the schools also. The second case study, it's not a mining site, but it's actually a former chemical plant site where rapeseed was grown to produce molecules for pharmaceutical industry. And then the third case study is about energy production from willow trees. And I wanted also to mention another case study that use hyper-accumulator plants, sorry. And it's a nice case study because it engages the community, the residents that are using gardens that are contaminated with former industrial activities. So it's a nice case study where the researcher and the community can work together to find solutions to restore contaminated land. But what is important for future project in Wallonia, and that what we would like to develop in the future is to implement combination of plant species and soil microbes. And what we would like to do is to use preferably native plants to minimize the use of fertilizer and water input, and also to select plants that are resistant to extreme events, because even in Belgium, as other regions in the world, there are more and more extreme events being either resulting either by water scarcity or heavy rain, and it's a major concern if we want to implement phyto management solution. So I wanted to mention another case study where we combined the remediation strategy. It was this project ended in 2023, and as you see in the diagram, what we propose in this project is that the remediation work that was performed by SPAC, which is a public agency in Wallonia in charge of the rehabilitation of brownfield sites. So they were in charge of the rehabilitation work, and in parallel, we were able to implement field experiments before the remediation work, during the remediation work, and after the remediation work. And the idea was to test the possibility to implement or to implement phyto management solution as a temporary use, I would say, because it's an opportunity for us to test a new solution, and it was very successful, and we managed to perform these 3 field experiments. Another point about the temporary use that I would like to highlight is that often, and it was mentioned several times in a few talks this morning, that because the mining site or brownfield are heavily contaminated, these lands stay for many years, like decades, abandoned and contaminated. And what we would like to encourage at the Walloon region is that instead of waiting for remediation, that we implement phyto management solution before and after the final land use of the mining site or any brownfield. Now I want to move to phyto management strategy for site affected by acid mine drainage. There is a very nice review from Thomas et al. Published in 2022. And in this review, they mentioned the use of phyto management strategy to extract rare earth elements, and there is like a list of plant species that have been tested in different countries worldwide, including Brassica napus or sunflowers, for example. So it's an emerging topic that I think needs more studies, but still I think of great interest. And then I wanted also to mention that recently in Korea, the phyto remediation or phyto management solution have been included in the National Sustainable Environmental Management Plan. So meaning that in the phyto management strategy are more and more used worldwide, and also we've seen also this morning that global mining companies are also incorporating phyto management strategy in their ESG framework. I would like also to highlight the fact that it's more and more the native plants that are more and more used in the different phyto management strategy. Here is some case study from Cyprus on the left, and then North Colombia or France or China. And in fact, the use of native plants is logical because they are adapted to the mining site, and they are also relevant if we want to develop phyto management strategy in the context of climate change. We need to make sure that the plant that we implement on the site will be resistant and resilient on the long term. And also we want to avoid water irrigation and all other input if we want to stay sustainable. And then before concluding this presentation,
one minute.
Yeah. I wanted to say a few words about the phyto management and PFAS, because PFAS are also found in mining areas, and there are some interesting projects going on the use of phytoremediation and phyto management to manage PFAS. And then I will move to the conclusion that phyto management are facing key challenges, but even if these challenges are complex, they should not stop us for deploying this solution, because it's imperative to remediate contaminated sites, and by deploying this nature-based solution, we are acting on all three levels: environmental, social, and economic. Thank you for your attention, and I looking forward to see you in Liège at Aquaconsol conference. Thank you.
Thank you very much, Cécile. Very good presentation, and good that you reminded the Aquaconsol conference. It's let's remember, from 16 to 20 of June of 2025, of course. Very good. We don't have any question from the chat, just one very short question from you, from me, let's say. pyrolysis or incineration, which could be the best final destination of the biomass coming from phytotechnologies, let's say. We know that are rich of heavy metals. There are some studies on pyrolysis. Some countries do incineration. What's your perspective, the perspective of Wallonia?
Actually, in Wallonia, the main focus on phytomanagement is on valorizing the biomass for construction. Because we focus more on the phytostabilization in order to avoid to have the contaminant in the shoot. So because we want to avoid to have this the problem of the contaminant in the shoot and not being able to valorize the shoot. So we are less developing the energy biomass and more the production of molecule, bioplastics and material for construction.
Thank you very much. Thank you very much for your answer. Now I hand over. Probably we will, an announcement, we will finish 15 minutes later, so 12:45, because also the next speaker needs its own space. So I hand over to Fred, because we are now jumping to the other part of the world, Latin America. So Fred, if you could introduce next speaker.
Thank you, Marco, and welcome to France, Cabanillas. So we are now moving to Amazonas and more looking at extraction, especially for mercury golds, and looking at clean technology. Over to you, Franz.
Thank you. Hello, everyone. I can share my screen. I'm not sure.
Yes, you should be able to.
Okay. It's okay?
Yes, just now put the diaporama.
Perfect.
You're good.
Okay. Hello, everyone. Thank you for the invitation. We will talk about our work in the Amazon, in Peruvian Amazon, to promote the elimination of mercury in the artisanal scale gold mining. Okay, it's a very big problem in all the entire Amazon, and now also for the increase of the price of gold, the Amazon receive a lot of pressure for the mining. Okay. Okay, we will talk about. I will talk a little fast some parts. Okay, because I know that we are late. What about PR, the organization that I work with? No, we are working in 27 countries. Okay, we specialize to work in lead, but also in mercury. We work in different countries around the world, not only in South America, also in United States, in Mexico, Ghana, some parts of India, Indonesia, Philippines, Bangladesh, and other countries in Africa. Okay. Why we focus on ASGM? First of all, artisanal scale mining is the leading cause of mercury pollution, okay, in different parts of the world, not only in South America. There is some important economic revenue for many people. 20% of the world's gold production comes from the artisanal scale gold mining, and an estimate value of $28 billion of dollar, okay, per year. Most of 15 million people in 80 countries active in artisanal scale gold mining. More than 100 million people depend on artisanal scale gold mining and directly for their livelihood. And women make up as much as 1/3 of global artisanal scale gold mining workforce. But we have harmful practices, deforestation, and mercury release, and most you can see that in the Amazon. We talk about more of Peru. Peru's government signed also and ratified Minamata Convention, okay? But we not still implement a plan to work in artisanal scale mining with mercury. What about Madre de Dios, the place that I will explain you now. Peru is the largest gold producer in South America, okay, and the 11th largest in the world. 70% of the Peru's gold production came from Madre de Dios, okay, related to ASGM. But the mercury also is still legal in artisanal scale mining in Madre de Dios and Peru. The miners can buy mercury, it's legal, okay? Madre de Dios has more than 140,000 people, okay, around the half of which are estimated to be involved indirectly with artisanal scale mining. Okay, there are the data that is important. Why is important Madre de Dios, but also, okay, 181 tons of mercury are released per year in Madre de Dios with the different operations in extraction of gold mining, and 115,000 hectares of degraded areas. Okay, this is an estimation until 2019. Okay, it's a lot of it's not only deforestation. When we talk about the impact of artisanal scale gold mining, is the degradation of all the ecosystem. You can see that in the picture. It was at the beginning, it was a primary forest, no? And also, why is also that important? Because all that activity with that important environmental impact is it happens in a Madre de Dios that also is a very rich biodiversity hotspot. Okay, we need to understand that because it's a very, very important impact. And with the mercury, it's more difficult to do some traceability because the mercury is like a silent contaminant. What about our work in Madre de Dios? Our approach to reduce exposures to mercury, we create some kind of 4 components, important components. One is the mercury-free techniques. Second is environmental aspects and reforestation. Third is the education, that is more like a transversal component. And the last one, for us, is more important. Is one important component is mine-to-market solutions. I will explain you after why is that important, no? What about the mercury-free techniques? Okay, the mercury-free technology, it begins with a mineral characterization. Pure works with local partner is a technical institute that has laboratories and also an infrastructure that permit to do that, to sample and analyze the mineral composition of the mining material in each mining concession. Okay. After that, we do the selection of technology using information from mineral characterization, and we select with the miners the most appropriate mercury-free technology to work. Okay. After that, we begin all the trainings, use and maintenance of equipment, because it's important that the miners learn how to do that, not depends anytime to the technical institutions. And also the smelting training, because it's an important way to commercialize the clean gold that they produce. In the first step is to work at the mining front, okay, with a very, very artisanal practices, but permit to be more efficient in that mercury-free process. After that, the material goes to the processing plant, no, without any chemical, okay? It's only the gravimetric system that separated the most heavy particles and the less heavy particles, okay, to get that gold. In this case, in Madre de Dios, in the Amazon, that gold, you can find the gold in the soil, but in the very tiny particles. No, it's not like for example, the mining in the mountains. It's like in this picture, no? You can see the gold powder. After that, the miners learn to smelt. No, normally they sell their gold with mercury in a very rustic piece. No, but now they learn to how they can produce a very good piece of gold, clean gold, without any mercury in the process, and also they began to learn how to transfer that in the jewelry articles. No. The second component that is important for us is the reforestation, no, and also the environmental aspects. Okay, it begins with the assessment, the characterization of the area, the degraded area where they worked, no, and we find with them some part that they want to begin the closure mining process. After that, we do the environmental baseline, no. We use drones for the orthomosaic. It's like to understand what happened with that landscape after the mining operation. No, like you see in the pictures, it's like patches of degraded areas, and we need to understand what happened after the mining operation. Okay, we do some soil samples and baseline to understand if there is some heavy metals there. After that, the second step is the management, design and planning of the reforestation process using the orthomosaic, the map that the drone can produce, knowledge of native species and adaptations of the Cincia method. Cincia is an institution that works here, is specialized in restoration process in that kind of degraded areas. Okay. And the last part is the planting, okay? We work with miners and local university students to do that. The last part, the last step is the monitoring. We create a database with the measurement of the height, the weight, no? And are taking of saplings of the moment of reforestation and the monitoring of the maintenance of that part of reforestation process. But here we use also cover legume species that we understand that are very, very useful to that kind of degraded areas, because it's like you see, it's like a sandy soil. They don't have, it doesn't have retention and are very, very poor in organic matter. Now, for that, we use the cover legume species like a complement for the forest native species. And why also is important the reforestation? We understand that because the role that the trees and also the cover legume species can have in that kind of degraded areas, we have two kind of important roles. The first is to avoid the transportation of the particles of mercury to the water bodies, okay? With the roots of that cover legume species and also with the forest native species, we can avoid that. We can prevent that with erosion, that mercury or different heavy metals can finish in the water bodies. But also an important thing is like they are already exist some studies that says that the primary forest can't capture the mercury that is in the atmosphere and can fix that in the soil, okay? And if we translate that to the reforestation, is the same role. It's for that, for us, the reforestation can have that two functions or that two roles with avoid the contamination of mercury to the Amazon ecosystem. No, for example, you can see that how is a degraded area in that kind of ecosystem, and how we plant with a design, with a specific design with different native species to create a connectivity between patches of primary forest, no, with a mapping, preparation, and design. And at the end, we do the reforestation with the same miners. Okay, they do the reforestation and they want to learn how to do that. No, it's not too easy. Like if you think about a closer mining, for example, in the desert or in the mountain. In this case, it's more difficult, no, because it's the Amazon. No, the impact is more intense and more complex to restore. Also, they implement a tree nursery. We use the bioshower also to improve the quality of soil, but also to prevent the contamination of mercury and fix that in the soil. In the case where we find some contamination in the soil. And we use other soil amendments to improve the quality of soil. And the education is like a transversal component in all that process. But we began to work with the miners so they understand also what happened with the biodiversity, why it's important, how they can do a soil and water quality sample in the field, and also to understand if they do that, they can access to a responsible market. Because I don't know if you remember in the beginning, I told you that it's very important to work with that, with the incentive. And this is the last part, is the mine to market solutions. This is a very interesting example. We work with AMATAF, is a mining association, that they became the first mine in the entire Amazon to achieve fair mine certification. It's a certification like, for example, with cacao, with, I don't know, with coffee, it's a certification, but oriented for the artisanal scale gold mining. And why is important? Because the mercury-free gold supply chain, we explore with them options for the sale of mercury-free gold, including through responsible jewelers and partners, for example, with Alliance for Responsible Mining, creators of the fair mine certification. Why is important? Because now, actually, in Peru, the mercury is still legal. Okay. Well, why miners want to change to a free mercury technology if they can buy mercury and they can do now mining with mercury? We need to work a lot of that, in that. And also we work we learn and also we work with them to understand what are the health problems that they can have and their families. But I think that it's important to work also in the incentive, not only in that part. We need to work in the incentive. It's the most real option for they can change to a mercury-free process. Okay, and also it's important to work. I don't know. Many of you maybe hear about Madre de Dios and the mining here. Maybe if you Google that, it's a lot of bad information, a lot of disaster, etc., etc. But we work with a formal sector that want to do the things better. It's important to understand that. You can see, how we work also in the communication part, to understand that there are miners that want to change, and they already do that. And what are the next steps for us in Madre de Dios? We began a very interesting project in January with a woman network of miners here in Madre de Dios. And what is the main goal? The main goal is to quit and eliminate the use of mercury and also work in the restoration of that degraded areas with the same model, the same way to work that we worked in the last few years. We are very happy to begin that project for 3 years. And I will talk about the conclusions. Okay, eliminating the use of mercury in artisanal scale gold mining in Madre de Dios is possible. Okay, we understand that it's possible. The miners can do that, and we already have miners who have successfully stopped using it. We have a very important group of miners now. Okay, responsible mining and the implementation of good mining practices in Madre de Dios should be more widely promoted and recognized internationally. Because if we don't create that, the promotion or the communication of that good practices, the miners can find that market that can incentive and that create that kind of how you say that responsible market. Okay, it's important to work on that. A key factor in replicating mercury-free methods is the commercial aspect. Without clear economic incentive, it is not feasible to scale up these practices to a large number of miners. We understand that, We understand that it's very, very important. Another important conclusion is that in Peru, currently in a favorable position to transition toward mercury-free artisanal scale gold mining practices and to establish incentive for miners who operate without mercury. Since mercury remains legal, we still have the opportunity to regulate its use proactively. If we want until it becomes illegal, as was the case in Colombia and in other countries in the Amazon, we risk creating a new problem, no? That is the emergence of a mercury black market. The solution is not to become an illegal or to transform the mercury in illegal, because the miners also look for the same option, but with another market, with a black market. No, we understand that. In Colombia, it's a very clear case of that. No, we think that it's important to now, in this moment, begin to create an incentive, to create that new market, to work and promote the responsible mining, and we already do that. No. We have a very important examples like you saw with Amataf, no, and they began to export their gold from Madre de Dios. They did the first exportation the last year to a refinery in United States, no, and we are very happy, and we think that it is the beginning to that, to wake up that responsible market from Madre de Dios to entire world. And I finished that. I don't know if you have any question, and thank you for your time.
Thank you very much, Franz, for that brilliant presentation and a very good example on how it's important to engage with the citizens and the local communities to promote some sustainable practice for the mining, and how it's important that benefit the local communities, not only for the environmental, but also the wealth, and also for the human health aspects. So it's a very good example, and it's great to see happening. I think what we're going to do, bearing in mind we are slightly running over time, perhaps is more to get you along with the other speaker, Franz, and maybe we should transition to the panel discussion. Is that good to do? And perhaps, so we were with Marco and having, and also with Valeria, some would like to ask a questions perhaps for our first speaker, Kirsty, Diego, and Franz, with our last speaker. We got some in towards sustainable mining, but how do you see the future of promoting more widely the sustainable mining, and what would be the best way to do it? And beyond what we are currently doing, is there, in your view, still a lot of, or is there still opportunities to do more actions? So we would like to comment on this. Maybe Franz, you were just speaking. Do you want to offer some insight on what you see as a need to, what could be done further for sustainable mining in the future?
Yes, I think that the case that I present of the place where I work, I think is a very difficult also context, no, because it's the Amazon. I think is and now, for example, with new legislations of European Union, it will be most difficult, no. At some moment, for example, I think that that deforestation could be not permitted for different activities, yes. No? And I think for the formal miners here in the Amazon, it will be a very, very important change. I don't know how it can work, but in the other way, I think that the important to understand that we have a formal sector, and a formal sector that works well, I think can open many doors. No, now I think we are one of the, if we are not the only, I think, but there are not too much institutions that want to work on that topic. No. Here in Madre de Dios, we have different institutions, research institutions, but most work to show what happened with the environmental impacts, but not too much with work with the solutions. No, I think for do some kind of sustainability in that process of good practices in mining or here in the Amazon, we need to be clear what happened, no? And to need to be clear to communicate that happens, no? That are miners that work with mercury, that they reforest, no? And we began to do that, no? I think this is the better way to that could be not sustainable, because for me the mining is not sustainable, but the good practices in the artisanal scale gold mining can be sustainable, no?
Yeah, so perhaps it's more on how we could be more caring and finding some compromise on maximizing the use of the minerals we want to look for, but also how we could maintain or mitigate the environmental impact of these activities. And I think one thing is very important also, we had across different part of the world, and very often I would think in Amazonas is quite a remote area, so the engineering approach that perhaps Kirsty proposed in Australia, that might be not feasible as such. So we need to also think, and perhaps Kirsty, I would invite you to, because some of what might be seen as a relatively sustainable approach for Australia might be not fit for purpose for Peru due to the environmental settings, and we could also perhaps think about Spain and Portugal. So what's your view, Kirsty, on this?
Yeah, absolutely, I would agree. You know, the Amazon is a very different location to where the Curry smelter was in Australia, and you know, we've had a lot of deforestation in Australia over time, and so the reuse of the land that's already been deforested, but to be reusing it for another industrial application is a good use of that land. And so we're on the smelter site, we're not relocating the problem to another part of the state or another part of Australia. We're able to keep to sustainably remediate that land and to impact on quite a small footprint within a larger area that can be redeveloped for another industrial use. But perhaps, yeah, like you say, that would not necessarily be suitable in a rainforest area, or, you know, where you have a mining impact that is also a small footprint, but you don't want to be impacting on other areas of land that are heavily forested.
Yeah, and I can see in the chat people are saying also, yeah, matter of scale too. I think scale is important. We heard also Marco saying in China, for one thing, also I had the chance to go to South Africa, and when you see site in Europe, and then maybe you go Australia or South America, all the scale is important, and what we see. So I think the scale is important, and perhaps when we think about the sustainability, is also perhaps thinking the next use when the mine is complete. So effectively, what sort of services, and perhaps thinking more about the next stage. So during the process, and then once it's completed, what could we do with these sites when the exploitation has been completed, and that probably join Diego talk about in Spain now, where they're thinking on how they could potentially give a new land use or purposes for this land. So it's good to see also this idea of using this phytoremediation approach. Diego, do you want to comment maybe?
Yes. Now in Spain, we have a big input to promote the mining activities because of we have a new strategy for critical materials recovery. So from our institution, we are trying to develop a strategy not only for develop novel strategies for the exploitation of the minerals, but also for the restoration simultaneously. So now we have make a guide, so how we can make exploitation of all landfills, trying to recover some minerals that were not extracted in the past. So we have dams with I cannot remember the numbers, but huge amounts of tons of mining wastes that we can recover some critical raw materials. We are looking for cobalt. We are looking for well, also for copper, lead, and zinc, but also for rare earths. And our idea is to restore these areas at the same time that we are able to extract these critical raw materials. So we have recently received big inputs from the Spanish government to make an inventory of the different landfills that there are mining landfills in Spain. We have detected some of them that are very potentially exploited. So our idea is to use the ore processing, mineralogical processing techniques to recover these elements and simultaneously reuse the new wastes for restoration. So in this part, we are making big efforts on the phytoremediation, trying to create different tools in the framework of the nature-based solutions to restore all these areas. So we think that now it's quite difficult to promote mining from the point of view of the society. So we are trying to use all the phytomanagement strategies to get the people closer to how we can restore, and we are not doing the bad things that were performed in the past in Spain. So this is more or less the currently point of view in our country.
It's a good point. So it's the concept of urban mining, and we had also significant project on landfill mining. It's just the costs. Very often you don't have, for the metals you want to mine within our urban waste is not high enough. So you have to combine with some resource recovery or extracting added value chemicals. So there is an interest around these. And I guess it's also, it might be not so popular to mine landfill site when they've been closed. So there's still a bit of challenge, but there's certainly interests also. I've seen in the chat you were talking about microplastic as metal. We're currently looking actually on how microplastics formation in landfill along leachates might be an option to mobilize the metals, and we could recover them more easily. So certainly a lot of development, I think, as often is the economics that is a bit of a challenge, and we need to probably get the mining with the manufacturing sector more working together and find opportunities to get this joint approach. But I would like to thank you for your contribution, and that is very good. Yes, Diego?
Sorry, Frederick. I would like to make one question regarding all the topics that we were talking about. When talking about the possibility of applying amendments from wastes, we have a big question in Spain now, because we were using sludge compost as an amendment for soil remediation in combination with phytoremediation. But now the change in the law 1 month ago is not allowing the application of sludge compost as compost. We need to apply as a sludge. So this is a big issue also from the presence of microplastics and how microplastics are also affecting the metal cycles with the plants. So I don't know if you can give us some point of view from other countries and how you are dealing with this topic.
I think it's too late, Diego.
It's very important.
Unfortunately,
Sorry?
it's too late. Maybe we can discuss this in Aquaconsole and RemTech Europe, maybe. I have a very last question, 15 seconds each for Teresa and Dave that I promoted so 15 seconds each. I recommend, because I was already advised to leave the room. Teresa and Dave, waste tailings and critical raw materials. Which are the opportunities? 15 seconds, really small comment.
Well,
Teresa first and then Dave.
Okay, I can say that the opportunities are enormous, and in Portugal, the situation is exactly the same that Diego explained for Spain. We are now trying to remining tailings and old waste dumps to extract critical raw materials. So we are a mining region with a long tradition, with enormous legacy that can be really recovered through valorization of the wastes in tailings and in waste dumps. I think it was more or less 20 seconds.
Thank you. Dave, very shortly, in the UK.
Yeah, thanks. I think I totally agree with that, but I think it's important also to understand the need for the environmental enhancement of the sites as well, and preventing the pollution that is coming from these sites as a primary objective. And then finally, don't forget that these sites have to be looked after in perpetuity, and so getting the aftercare right and the ongoing management right is something that often gets forgotten about in the excitement of resource recovery and commercial redevelopment of sites. So
thank you both for your comments. Sorry to be so short, but we have a little to leave. Also, Fred, thank you everybody for this. Valeria, we want to say something to in the end, very short, 10 seconds.
Thank you to every speakers and also for the people that attended in presence to Taranto. Thank you, Marco and Fred, for your collaboration. Thank you.
Thank you all the speakers. Thank you, Fred. Also 16 to 20 June, Liège. RemTech Europe, 15 to 19 September 2025, Ferrara. That's all. Thank you very much. Thank you very much. And
thank you very much, everyone.
Thank you.
Thanks so much.
Thank you.